So thank you very much, Monica, for inviting me here. I'm going to talk today about work done in collaboration with my excellent student, Pushkal Srivastav. He did many of the hard calculations, but of course, all the criticism I would like to. That's my responsibility. Whatever criticism you have of this. So I'm going to talk today about the Fuzzball program, and I know this is one of the centers of research on fuzzballs, and so I'm glad it's a small enough informal group, so we can have a discussion. So please feel free to interrupt, and I hope we can make some progress. Okay, this is how I try to organize my talk. I'm going to give you an overview, and then I'll talk about some general aspects of fuzzballs from a statistical mechanics point of view, and then I'll talk about some specific calculations in two-charge fuzzball solutions that were found a long time back, which started this program, and then some multi-charge fuzzball solutions that were found by Benna and many others here. Okay. So just so that we're on the same page, let me just describe what I mean by the fuzzball program, because this is a term that's used differently by many people. So this is what I understand by fuzzballs. So fuzzballs are classical solutions which have the same charges as a black hole. Now fuzzballs look like a black hole at long distances. If you're far away, the metric looks like you have a black hole metric. But the critical difference, as far as I understand, between fuzzballs and black holes is that fuzzballs have no horizon. Okay, now one thing which is very clever about the fuzzball solutions is that you might have worried, how is it that these horizonless geometries are stabilized against gravitational collapse? And the fuzzball solutions are clever because the way they avoid gravitational collapse is roughly by taking some extra dimension and making this is a cartoon, of course, but making the extra dimension pinch off. So if the horizon was going to occur at RH, the extra dimension pinches off somewhere before the horizon occurs. And as a result, space ends, and so there's no possibility of gravitational collapse. Okay, so that's how they avoid the no-hair theorem. What's this? Very good. Okay. Very good. Now, of course, I had some cartoon about how this extra dimension pinches off, but really the extra dimension can shrink to 0 in many different ways. And so fuzzballs have structure. There isn't one fuzzball solution. There's one black hole solution. Or there's some finite, small number of black hole solutions, but fuzzballs can come in many shapes and sizes. And what I understand by the fuzzball program is that if you look at these distinct solutions, then these distinct solutions are the true microstates of the black hole. Okay, that's statement number one that I understand. And second, the claim is that as a result, this also suggests that black holes have no interior, because if fuzzballs are the true microstates of the black hole, then this means that the regular Schwarzschild solution that we tend to think of, which has a smooth interior, is really not the right way to think about the interior of black holes, but rather if you tend to fall into a fuzzball, at some point you hit this end of space. Okay? And in some sense, I'm really going to be interested in this aspect of the solution. The reason that I got interested in looking at fuzzballs was because I wanted to understand what the fuzzballs could tell us about the interior of the black hole, and whether they're a valid way of gaining information about the interior of black holes. So this is really the claim I would like to address. This is roughly an outline of my argument, which I'm going to try and outline.
Actually,
yes.
I missed it. What do you mean by this being the true microstates of the black hole?
Well, these are the microstates. Are you worried about the word true? These are the microstates of the black hole.
Classical solutions, so they can only correspond to some coherence.
So coherent states can span the Hilbert space. So you have coherent states, and so coherent states can be true microstates of the black hole. You have coherent states, you quantize them, you get the black hole.
There's some distinction between fuzzballs and microstate geometries and microstates.
Yes, I know there's a distinction.
Try to make it quite clear in quite a few of our papers.
Yes, yes.
So usually people mean by fuzzball highly quantum, highly fuzzy, non-describable stuff. Microstate geometries are things that you can describe using classical.
Yes. I'm aware.
So I think what I'm here is the microstate geometries.
Well, so
do
here.
you have anything to
well, I'm not sure. Well, so as far as I understand, stuff that has been made precise, a statement about these microstate geometries, yes. which is what is being, and the question is whether that's the only thing which is known. Now there are some other terms which you can use for other states, but the question I really want to ask is,
I think what Emil has, for example, for the D-5, you can also have microstate solutions, meaning solutions of string theory, which was not described as supergravity.
Yes, but so I don't care about supergravity. I'm happy if they're classical solutions, which may be classical solutions in string theory. But it's true that there might be some enhanced set of states which are maybe some quantum. So nowhere here am I saying that these are solutions in supergravity. If they're solutions in classical string theory, that's fine. But the real question I want to ask is whether by studying these solutions, which is really what we have, these classical solutions, do we gain some insight about the interior of the black hole? Okay, can you, for example, argue that black holes have no interior? Okay. So now this is an outline, a gist of my argument. So I'm going to make some limited claims, but these are the claims I'm going to make. I'm going to say that if you look at general statistical mechanics considerations plus some simple physical assumptions, which I will outline, these suggest that if you look at black hole microstates, then these black hole microstates, either a basis or typical states, cannot be represented by distinct reliable geometries, and they may be distinct reliable geometries either in string theory or in supergravity. As a corollary, fuzzballs cannot serve as reliable indicators of the nature of the black hole interior. Okay? I'm not saying at all that fuzzball solutions are, fuzzballs are states and they are good states to study in ADS-CFT, but the question I want to ask is whether they can serve as reliable indicators of the nature of the black hole interior, and I'm going to try and argue that they can't. And I'm going to give you some general arguments. So this is the first part, but then I'll try and give you some specific calculations if you don't believe my general arguments, which will try and bolster these general arguments in various sets of fuzzball solutions.
And it's about zero temperature black holes or finite temperature black holes?
These are BPS black holes. These are solutions which have been found.
No, but indicators about the black hole interior.
Well, the general statement I'd like to make is, of course, about finite temperature black holes. The specific calculations I'm going to do on BPS black holes, because those are the cases where I can do specific calculations. Okay, so let me start by giving you a statistical mechanics appraisal of fuzzballs. So as I said, this is how so this is the first part, which is some general arguments, and then I'm going to talk about the two-charge fuzzball solutions, the Lunen-Mathur solutions that started off the fuzzball program, and then I'll talk about these more recently found class of multi-charge fuzzball solutions. Okay, good. So let me just outline a few basic StatMech results, just so you're on the same page. So the first result I want to talk about is what we mean by typical states. Okay, so typical states are something which is a word which we use often when we discuss black hole microstates. Let me just say something. This is something which everyone may agree with, but just so we're on the same page. Let's say we have a big Hilbert space, and on this big Hilbert space, I pick some subspace of the Hilbert space, which I'll call HE. In the end, I want to think of HE as a space, of states between a given band of energies. But you don't have to think of it like that for now. This is just a big subspace, and it has some big dimension, which is e to the s. Okay? Then on this subspace of the Hilbert space, there is a sense in which you can pick typical states, and the sense in which you can make that precise is by picking typical states with what's called the Haar measure. Okay? The Haar measure is defined by taking this unitary group u of e to the s, taking any state in this on this subspace. The unitary group maps you to any other state you want in this subspace, and you can write down a Haar measure on that unitary group. That Haar measure is the Haar measure on this subspace. Then if you pick a typical state on this subspace, then the following results are true. First of all, if you take any operator A, you take any observable A, the expectation value for that observable that you get by averaging over all states with the Haar measure is given by the trace of that same observable, the expectation value of that same observable in the maximally mixed state. Okay? So this density matrix is the density matrix of the maximally mixed state, where PE is the projector onto HE. And the claim is that even if you take these pure states, these are pure states, and you compute the expectation value of A in these pure states, and you average that using the Haar measure, you get exactly the same answer as what you would get in this maximally mixed state. Okay? Now you might have thought that maybe that happens because pure states, pure states are very different from the mixed state, and somehow the answer averages out to the answer in the mixed state. But in fact, that's not the case. If you take this expectation value in any state, you subtract off this mean expectation and you square it, so you're looking at the deviation from this mean expectation, then this deviation is exponentially suppressed. Okay? It's exponentially suppressed by this factor, which is this ensemble fluctuation divided by the dimension of the Hilbert space. And the ensemble fluctuation, which is something that will appear again in my talk, is just given by the fluctuations of this observable in the mixed state, in the maximally mixed state. Okay? So this is the statement that typical states picked with the Haar measure are exponentially close to the maximally mixed state.
How do I solve this with Brownian motion?
How do you what?
How do I square this with Brownian motion? Because Brownian motion, so if you look at ensemble, for example, if I look at the air in the room, the density matrix just gives me a perfect fluid. And if I look at the typical state,
Very good.
and of course if I make a macroscopic measurement, then okay, it's exponentially close. But I don't think it's exponentially close, but okay, that's something. But then if I go to the scale of the mean free path, then I see molecules
is because
so
you
I'm not exponentially close.
no, because you're thinking of classical microstates. You see, the typical
The air
state.
in the room is a
Yes.
classical.
But the typical state is a superposition of all of these states. You see, you're thinking of classical microstates, where one microstate is given by some definite particle of the positions, by some definite positions of the particles, and another microstate is given by another definite position of the particles. But quantum mechanics has more space. So the typical quantum mechanical space state is actually a superposition of all of these different states. And if you take a superposition of all of these states and you make a measurement anywhere, that will indeed be exponentially close to a measurement somewhere
But
else.
then I shouldn't take Brownian motion by this.
No.
Brownian
So
motion shouldn't exist.
no. I don't understand why you
How
said
do I
that.
measure Brownian motion in this language?
What do you mean? You're looking at classical microstates. I'm not saying that there is no such
I'm
thing.
looking at the air in the room. So
I'm not
to
saying
measure
there's no.
Brownian motion,
Sorry.
it
Just
should exist.
1 second. I'm not saying there's no such thing as atypical states. You see, all of us are in atypical states, and the fact that I can measure you or you can see me is obviously means you're not seeing something which is an average.
No,
This
if
is
you look at the air in the room, no, something else. If you look at the air in the room,
Yes.
and I look at the scale, I make an experiment on a very small scale.
yes.
I'll see the molecules hitting me.
You're not in a typical microstate.
No,
If you
I'm
no. If you're in a typical this is a trivial theorem to prove. If you like, I can just prove it for you right now.
No, it's not a matter of proving.
But this is, I mean, this is a.
phenomenon. There's some physics which you are ignoring. because
No, I'm not ignoring any
measuring
physics.
Brownian motion.
Yes, but you're not.
Experimental.
Yes, of course
So
you measure.
Now they tell me that the air in the room is not described by quantum
This
mechanics.
is this.
Or
No.
there's something wrong with our-
No. This is the statement that the microstates of the room that you're looking at are not really. If you looked at typical microstates, which were linear superpositions of all the possible microstates in quantum mechanics, you will find that there is no way by looking at simple observables to distinguish between them. I mean, this is a very. If you like, we can just prove this theorem right now.
No. But the question is, again,
I'm not ignoring any physics. You're looking at atypical states. Of course, you can look at atypical states which have all sorts of physics.
But it's not that Brownian motion is a feature of all systems.
Sorry, Joseph, what are you objecting to?
Brownian motion is something which I measure. I take a small molecule and I trace it to some guy. I give it to a guy. I put the molecule in the room, and I see Brownian motion of the molecule. According to this argument, Brownian motion should not.
No, I don't see why. This-
How does that follow?
Because there's an exponential. So the distinction between a typical state in the hard sense. So the air in the room has the typical states, which are some quantum proposition of all the molecules, and essentially the difference between that typical state and trace of rho to the a, or rho times a, which is just fluid mechanics, which is just assuming that the air that is made of a continuous fluid, is basically exponentially suppressed.
Correct.
So Brownian motion should be exponentially suppressed and never measured.
I don't see why Brownian motion should be.
No. This is a statement about what's the difference between measuring Brownian motion in a typical pure state of the air in this room versus the density matrix of all possible states of air in the room. It's not some statement about
That's true, yeah.
approximating the air in the room by a continuous fluid. That's something different. Okay, this is just a statement about averaging over all possible states of the air in the room versus picking a single particular pure state and conducting this measurement.
So if you think of Brownian motion as exciting something, then that's indeed true. Alternately, if you just think of the air at equilibrium and you want to make one single measurement, then it's true that the measurement you would get by measuring in pure states and averaging over them is the same as the measurement you would get in a mixed state.
But the pure state, but the mixed state is not molecules. The mixed state is just a fluid.
No, mixed state is take any possible pure state of air in the room
And take a superposition.
and take a superposition.
But the mixed state. But can I say something?
But
If
the
you
question is,
if
can I
you
see in the mixed state any granularity?
Can you-
Does mixed state break
Absolutely.
translation
if you excite the mixed
Does the
state, you will
mixed
see.
state
If you excite the mixed state, if you hit it with a source, you will get the same 2-point functions that you would get in a pure state. But can I say it's true? You may be right in a sense that the mixed state is is in a fluid. If you really put yourself in a typical microstate, which is a superposition of all possible states, then it's true that it will be very hard for you to see a state where you distinguish atoms at one point, because the true superposition of states has a superposition of one atom being here and the same atom being somewhere else. So it's very hard for you to distinguish the true superposition.
Which then I can never prepare. I mean,
No, of course you can prepare. I'm not saying there are no atypical states. I'm not saying that all states are like this. So just
the molecules in the room
let me
are
just go on. Let me
typical,
just go on.
in our room.
Let me just go on to the next slide.
Typical, then
Let me just go on. Okay, so the way you should interpret this theorem, and maybe this is what we're discussing, is that most states in the if you take the Haar measure, are very close to being typical. That doesn't mean there are no atypical states. There are, of course, atypical states. There are states, you know, we are in an atypical state. The fact that we exist.
The air in the room.
Yes, the air in the room. If you take, you know, if you take some air where there's some definite configuration, some classical configuration, that's an atypical. Where you have a classical configuration where you can identify some red atoms being here and some other atoms being somewhere else. That's not a typical pure state. A typical pure state is one where you take a superposition of, you know, marked atoms being everywhere. So the moment you take, you know, you take one of these approximately classical states, that's some coherent state. And that coherent state is not a typical state in the sense in which I defined it. It's a state in which, you know, you have distinguishable atoms and you can distinguish atoms in one part from another part.
No, but again, if I have a box which is prepared as an experimentalist.
But sorry, I just want to understand what is the objection? What is the we can just prove this theorem.
No.
And then let's.
There's an objection either the way you are measuring, either the way you define.
But you have to tell me you have to tell me what the objection to the equations here is.
No. There's an objection either by ignoring the coherence.
But I'm answering the question. You're looking at.
Experimentally, again, I have a typical state of the air in the room. I should observe Brownian motion. You are saying.
But you will observe Brownian motion. How are you going to observe? What are you going to do with Brown? You're going to hit the state with some source and observe the response.
I have the air in the room, which
yes.
is in a typical state.
Yes.
I look at a small molecule, which
yes.
I paint in red.
Which you paint in red.
But that's one molecule.
Right. That now this situation where this molecule has a definite position.
No, it's a molecule of carbon. It's a different molecule. It's not a molecule of the air. So the air is in a typical state, and I have a probe which I paint, which is just some wolfram. You know, take some other material, which is not air. Now, if I look at the molecule in the fluid,
very good. Now, one second. So my pure state that I'm going to talk about is going to involve, you know, superpositions of this atom being everywhere. So the typical pure state, the really typical pure state, is not going to have this red atom sitting at one particular point. It's going to be sitting.
Operator A is defined. I look at the Brownian motion in the.
What is A going to do? Is A going to insert one of these red operators at some point? Very good. So then there's no. Very good. Good. So now this A inserting one of these red atoms at one point, the statement is that you will get, you know, if you do that in one pure state, the same result as if you do that in another pure state. This Brownian motion you observe will be the same in all of these different pure states.
The density matrix you are having
yes.
is actually continuous fluid. The density matrix description of the air in the room is a continuous fluid. It has no translation. There's no breaking of translation invariance in the density matrix.
That's
okay. So but there are still fluctuations.
There's no breaking of translation invariance.
That doesn't change.
Never give any
No. That's not true, because it doesn't. The fact that you have a doesn't mean that there are no 2-point functions. The statement is that you would measure the same thing if you put the red atom here or if you put the red atom there. That's the statement about translational invariance. It doesn't mean that once you put the red atom here, there are no fluctuations. You don't have translational invariance doesn't mean there are no 2-point functions. There are fluctuations. You know, the fact that you have, you know, this doesn't say that there are no fluctuations. This says that if you took one pure state or another pure state, you would get the same answer. And the fact that there's translational invariance is a statement that if you put this red atom here or red atom here, you would observe the same Brownian motion in both situations. The mean state does see fluctuations. In fact, the sigma ENS is a measure of these fluctuations. This is your Brownian motion observable. This is an order 1 observable. This is a measure of fluctuations in the mean state. And this is not 0. But the difference of the typical pure state from the mean state is suppressed by this order 1 quantity divided by e to the s.
Yeah, it's a statement that the deviation between a Brownian motion in a pure state and Brownian motion in the density matrix is exponentially suppressed. It's not that each is one of them 0 and the other one's not 0. It's the statement that they're both non-zero and the difference between them is exponentially small.
Mm-hmm.
Yeah.
Typical pure state, yes. Okay, is that good?
Okay, maybe then the density matrix calculation.
Maybe you're referring that the atypical states where these two numbers would be.
No. But then indeed, but then you're basically saying that the density matrix can actually get Brownian motion.
I think so, for sure. Because the air in this room could be in a mixed state. You know, it could be completely entangled with something outside. In fact, it is probably in a mixed state, right?
But
we don't detect the fact that the air in this room.
The usual way people calculate this by taking the
No,
density.
that's calculation, but that's a way of calculating. But you know, but it's and its trace, for example, has so the translation invariance of rho. Rho is an operator translation invariance.
Sure.
It's not only
if the room is infinite, it has translation invariance. Yeah.
No, sure.
And that's the statement that Brownian motion one place is same as Brownian motion another place. Which is true, right? You can't detect your position in space-time by measuring Brownian motion.
No, but this is saying that, you know, essentially this is just ignoring the fact that the air has molecules. So the moment you have that,
No. But as you said, you compute some partition function, and you would be able to compute fluctuations in this partition function, and that's what will give you this Brownian motion. Okay. Okay, so this is how I think you should interpret the statement. It's a statement that you have a Hilbert space. The Hilbert space has a lot of volume. You should think of Hilbert spaces as balls, as spheres actually, and then on in many dimensions, e to the s dimensions. And most parts of this space look almost the same as any other part. Okay, so that's all of this red volume. And of course, that doesn't mean there are no atypical states. There are some atypical states. We are in an atypical state, but the volume of these atypical states is very small. It's exponentially suppressed. So there could be, of course, states that differ very significantly from the mixed state, but if the volume of these states in the Haar measure is very small, and most states differ very little from this mixed state. Okay, so that's the way you should think of this theorem. Okay, what does this mean first for the fuzzball program? Once again, this may be something all of us agree with, but it says that let's take this A to be the metric operator at some point. Then what this says is that expectation values for the metric in almost all black hole microstates. Now, when I say black hole microstates, I'm looking at superpositions of the kind I defined previously with the Haar measure are exponentially close to each other. Okay, that in particular means that if you look at almost any Haar typical microstate, which is almost all of the volume in the Hilbert space, that corresponds to some universal average geometry, which comes by looking at the metric value about which all of these values cluster. Okay, so I'm saying that if you compute the metric operator in any black hole microstate, that gives you almost the same answer in one microstate and in another microstate. The answers are exponentially different between, exponentially small, the difference between them. And this tells you that almost all microstates you should think of as corresponding to some single universal geometry. Okay? So now the question is, what is this universal geometry that represents most typical microstates? So I'm going to make a physical assumption here, which is I think a non-controversial assumption, but we can discuss it if there's questions about that. I'm going to say that the conventional black hole geometry, after incorporating classical string theory corrections, this correctly computes the average value of bulk observables, including the metric or correlation functions of the metric. That's because correlations functions of the metric can be thought of as a product of the expectation values of two metric operators, which is for which the previous theorem also applies. And I'm going to say that this average value of bulk observables can be computed by the conventional black hole geometry, perhaps after incorporating classical string theory corrections. And I'm going to make another allowance, which is I'm not going to demand this once we are within Planck length of the horizon. Okay, so if we are, as long as we are more than Planck length away from the horizon, I'm going to say that averages should be well computed by the black hole geometry. Yes?
What sort of correlation functions are you looking at?
2-point functions of the metric is what I'll look
But
at.
at fixed time?
For example?
Because I would think that if you start taking time separation to be too large,
Yes.
then maybe
If you start taking the time separation to be right, so the previous theorem fails if this sigma ENS, which is trace of rho a squared minus trace of rho a the whole squared, if this becomes exponentially large. Okay, so if sigma ENS, can you see this? Yeah. If this becomes e to the s, then you get into trouble. Then an operator which has such large fluctuations can actually distinguish between pure states and a mixed state. So indeed, if you take A to be a product of two metric observables, so that the fluctuations in this are so large, are exponentially large, then you would run into trouble. Okay.
Why are the this correlated that I was telling you about? Why are the fluctuations so?
Well, you would have to compute the difference between the 4-point function and the 2-point function, and the square of the 2-point function. So if the correlator becomes very large, if you take your separations to be, I'm not sure, you might need to take them to be of, I'm not sure how large you'd need to take the separation, but it's certainly true if you take the separations to be large, just because of chaos, you might worry that this fluctuation might become very large, and so you might start seeing differences. But I'm not going to do anything like that. I'm going to take simple 2-point functions of the metric and things which you can measure in the geometry. Okay, so simple observables which don't have exponentially large fluctuations.
What do you mean by Planck length from the horizon? If you have an extreme black hole, for
Thank you.
example, the
Good.
horizon is infinite,
Yes,
so
yes, very good. So what I mean by Planck length is so this is an imprecise statement right now. I'm going to make it more precise in a second. But this is but here's what I mean by Planck length. Let me do it now. So in principle there's some area that you would use to measure what the horizon would have been. When that area is RH plus L Planck squared, that's what I'll call Planck length. Okay. So if you have some long throat at the point where the area of the S2, if you have some ADS2 cross S2 throat, at the point where the area of the S2 becomes RH plus L Planck square, that's where I'll stop demanding this from happening. So this will allow your long throats. This is basically to allow so yeah.
Is the redshift to that point 1 over s or e to the minus s?
I think the redshift to this point is 1 over s. Okay, so that's whenever I say Planck length from the horizon, I'm going to measure it by looking at the physical size of some transverse space. Okay. Okay, good. So now I think this is not a very controversial assumption, but let me just address briefly the question of what if this average geometry is not the conventional black hole geometry. Okay, someone might say that even the average geometry is not the conventional black hole geometry. If that is the case, then we have the following questions. The first question is that many correlation functions of the metric are obtained naturally from continuing the Euclidean calculation. Okay, doing in particular time ordered correlators of the metric, including equal time correlators. You can also get by doing the Euclidean computation and continuing that. And so if someone is to say that this average geometry is not the black hole geometry, then one also has to explain why the Euclidean saddle point is not a good saddle point to compute correlation functions of the metric. Okay, so now people sometimes say that the usual Lorentzian saddle point is not a good saddle point because it has a singularity, but the Euclidean saddle point doesn't have any such singularity. Second, if someone says that the average geometry is not the black hole geometry, then in ADS-CFT it would mean that correlation functions in the conformal field theory should be compared to averages computed in this other universal geometry, whatever it is. Someone has to tell me there is a universal geometry by this theorem I told you previously, and someone has to tell me what that geometry is if it's not the black hole geometry, and it would say that correlation functions have to be compared to correlators in this other universal geometry.
Some things which depend a lot on the structure. So for example, you have these log numbers. So for example, if you look at neutron stars and you look at their response to fluctuations, or for example, if you look at the Kerr black hole, the Kerr black hole comes from just spinning vacuum. But if you spin a structure which is horizon sized, you can get, depending on the features of the structure, make actually different dipoles, quadrupoles, octopoles ratios than you get in the Kerr.
So these are not typical states, right? The typical state, in fact, is just a Schwarzschild black hole. If you could yes, but if you look at the typical state that dominates a given energy, that's just a Schwarzschild black hole. Now you could fix some other charges. You don't have to be in a microcanonical ensemble. You could fix some charges, and then you would get some geometry that dominates the averages, and that geometry is, I would expect is the conventional black hole geometry.
Would it have to be a geometry, or?
I think it would have to be a geometry because well, it would have to be. So are you asking, does it have to be a classical geometry?
I'm asking, yeah. It's
good. One reason.
I've been asking because it's again,
yes.
If I have a Kerr black hole, if you look at the Kerr black
yes.
hole, the Kerr black hole is an infinite number of dimensionless quantities which are characterizing the black hole. If I imagine, replacing the black hole by something, even if in the hard typical sense it will give me some geometry, whatever I'm replacing with, has some internal structure, some equations, so I could get different numbers.
Well, the question is if in the hard typical sense, so maybe the question you're asking is in the hard typical sense, do you get a geometry? One diagnostic of whether you have a classical geometry or not is to look at correlation functions and see if they factorize. If correlation functions factorize, that's the sign that you're in a classical geometry in the bulk. And the fact that correlation functions factorize in ADS-CFT just follows from standard large n counting arguments. Just standard large n counting arguments tell you that you look at correlators of the stress tensor, they factorize to leading order in 1 over n. And so that itself tells you that whatever you have in the thermal state, dual to a thermal state, is a geometry because correlators factorize. So that's a sign of the fact that you have a classical geometry. Okay, so now this was considering the possibility the average geometry was not the conventional black hole, which I'm guessing nobody is objecting to. So I will assume that the average geometry is the conventional black hole. Now if you grant me this, let me just say the following. So the average geometry is a conventional black hole. So now if you grant me this, then we have the question of understanding, so what are fuzzballs doing? So perhaps, and I'm hoping that this is the correct interpretation of how to understand what fuzzballs should be thought of, is that perhaps fuzzballs should be thought of as a basis for the Hilbert space, not as representing typical microstates, but as representing some set of microstates so that any microstate can be given as a linear combination of all of these fuzzball solutions. Okay? That would be the statement that fuzzballs form an atypical basis. Now let me point out that in fact a basis can consist of atypical states, and that's because the set of elements of a basis is actually finite in number, and it actually occupies volume 0 in the Haar measure. Okay? So there are e to the s elements of this basis, of this e to the s dimensional space, and these e to the s elements are just e to the s vectors, and they actually are volume 0. So you could have in principle an atypical basis. And so perhaps the way we should think of fuzzballs is by saying, well, the typical microstate is described by the black hole, but you have these fuzzballs, and these fuzzballs are atypical elements, and they are somehow the basis you should think of, and you should think of typical microstates as being superpositions of all of these fuzzballs. Okay? But now I'm going to point out that even a basis cannot be too atypical. Okay, you can't have even a basis being too atypical. Okay, why is that? So here's another result. Remember, this was sigma ENS that I defined previously, which was the ensemble fluctuations. So let's say I have this sigma ENS squared actually, sorry, okay, which measures the fluctuations of some observable. And let's say I were to give you an observable. I'll come to what kind of observables this has, what kind of observables satisfy this property shortly. But let's say I were to give you an observable where the fluctuations compared to the expectation value in this mixed state are suppressed by some power of s, okay, where alpha is some positive number. Okay. If I were to give you such an observable, then the following result holds. Let's take some elements of a basis. Let's say there's some basis which has elements that go from v alpha 1 to v of alpha e to the power s, and let's say the first m elements alpha 1 to alpha m are such that this expectation value of the observable A is very different from this mean expectation value in this mixed state. Okay. So these are the atypical basis elements. Then if this observable satisfies the property that its deviation divided by the expectation value is suppressed, then you can show that this number of atypical basis elements divided by e to the s vanishes at least as fast as 1 by s to the 2 alpha. Okay. So if you can find an observable which has the property that fluctuations are small compared to its classical expectation value, then for such observables almost all basis elements are typical, okay, are very close to the mean. Okay. Now the observables that have this property are precisely observables which are classical. Okay. In particular, we can use the conventional black hole, because sigma ENS is computed by looking at fluctuations in this average geometry. We can use the conventional black hole geometry, which remember we agreed computes averages for us, to estimate what sigma ENS is. And in particular, if you take A to be the metric operator, just a metric operator at some point which is well separated from the horizon, then you can estimate what sigma ENS is. This is just an estimate that uses Hawking radiation, the fluctuations due to Hawking radiation, and you can show that sigma ENS by the expectation value of A, if A is just a metric operator at a point away from the horizon, is 1 over square root s. So the metric operator at a point away from the horizon is one of these observables that has a small fluctuation compared to its classical expectation, and that's not surprising, you see, because in ADS CFT language, the 1 point function of the metric, the 1 point functions are order n squared. Okay, whereas 2 point functions which calculate the fluctuations are order 1. Okay, and that's why if you look at 2 point functions divided by 1 point functions, that's a small ratio. And so the metric operator in particular is one which satisfies this property, and this tells you that almost all elements of a basis must be close to the mean value if when you probe them with the metric operator. Okay. So the metric operator in almost all basis elements should be close to the metric in the black hole. Yes.
So on the previous slide, you required that the fluctuation in so when you take the expectation value of A in this basis.
Yes. A in this row. This expectation is A in this row.
No, I meant the lower equation. So
this one.
That equation tells me that this observer can have an order 1 difference.
Yes.
Can you?
You can make it more precise. It's made more precise in the paper.
Like down by a power of
yes. So yes. So if this is suppressed by 1 over s to the beta, then this is down by 1 by s to the power 2 alpha minus 2 beta. If you look at elements where this guy is suppressed by 1 over s to the alpha, 1 over s to the beta, where beta is some other number, then
so
the number is 1.
Alpha, then,
that's right. So if beta is equal to alpha, then you're done. But that's the statement, if beta is equal to alpha, then this is the statement that most basis elements are within 1 by s to the alpha of the mean. So that's fine. That's the statement that most basis elements are already very close to the mean. Okay.
There's a question about this basic. So there's another way to look at. I'm confused about the point far away where you're looking at.
This doesn't have to be very far away. I just meant well separated means not within Planck length. You can go even within up to string length of the horizon. I don't mean a point far away.
But is it?
I just mean well separated in that not within Planck length.
Because I think if there was separation of, I have to look a bit at the way you define this, because again, when you have a very long throat with something at the bottom, the distinction between two things which are at the bottom can be over the 1 over n, 1 over s, even if your observer is up the throat. even if you are, at the bottom of the throat, you have huge differences.
Yes.
But because
That's
of,
right.
of the huge redshift, the distinction can be over.
So I really want to look at the metric operator at some point. Or you have to make some nice coordinate invariant operator if you like. But we can, let's for now just think of components of the metric. So I really want to look at how close. You also have to be a little careful in defining this, because you have to have a gauge invariant way of defining what the point is in different geometries. One way to do that is do that by a relational prescription. You start at some point in the boundary, you fall in with some geodesic for some time, you measure the metric operator at that point, and then you can compare the metric operator you get in the black hole to the metric operator you would get in another geometry. And I claim that provided the metric operator at that point in the black hole has small fluctuations, which it does almost, which actually it does even when you are at the horizon, okay, then the metric operator in most basis elements should be close to the metric operator in the black hole. So this in particular applies as long as you're not within Planck length of the horizon.
So if I'm considering one of these smooth geometries,
yes,
and I make a perturbation of it, where
yes,
locally, so in all these geometries, the curvatures are relatively big everywhere.
Small. Yes.
So the radius of curvature is large.
Yes.
So if I make a little localized perturbation and say, the metric deviates from the background by, x.
Yes.
Okay. Does it matter for you where that perturbation is made, whether it's down in the cap of the geometry or somewhere far up?
Actually, what matters?
Because locally it doesn't make much difference, and I would say sort of locally, a deviation of the, a bubble, a little dimple on the space, makes a deviation
of
geometric
order 1.
Of order 1.
Yes.
No matter where it is.
Yes.
But I think for people who are enamored of fuzzballs, it makes a big difference whether that perturbation is made, way up the throat or way down.
No, I want to disallow perturbations that are made way down the throat as well. As long as you're, I want to say that those cannot correspond to typical basis elements. Of course, you could have atypical.
So I think
yes.
what I mean is asking is
so could you have? Well, the question I'm answering is: could you have basis elements in which the metric down in the throat differs significantly from the metric of the black hole? Could it be that the black hole metric has something like this, and the basis metric has something like this? This may be deep down the throat. Very good. So now
nothing else.
And nothing else. So this guy may be caps off here, right? Very good. So now I'm going to take A to be my metric at this point, which is some distance down the throat, is G at this distance down the throat. And the thing I need to estimate is whether in the black hole geometry, fluctuations of A are large or small. In general, fluctuations of A in the black hole geometry are always small. In fact, they're even small once you go right to the horizon. And so if fluctuations in the black hole geometry of A are small, then this just by computing 2-point functions. You see, you can compute this sigma ENS is just a question of computing 2-point functions and subtracting this out. So this is just a question of computing 2-point functions in the black hole geometry, and those 2-point functions you can compute. You see, the moment you allowed me the fact that averages were computed by the black hole geometry, the trick here is to recognize the fact that if averages are computed by the black hole geometry, then you can also compute ensemble fluctuations by going to the black hole geometry.
But not at the scale A, averages are computed. So you're trying to, so if you go away from the scale A, so if you go like,
Is this at L Planck away from the horizon?
No.
So my question
so this
was,
is, yes.
My question was basically,
It's
let me take some
distance,
spatial component of the metric.
Yes.
Okay, and make a wiggle in it.
Yes, yes.
Okay, and I make the same proper size wiggle, okay, but I vary L. Does your sigma ENS depend on L?
I didn't understand the question. You vary L between what and what?
So L is how far down the throat you make this perturbation.
Yes.
Okay?
Yes.
But the perturbation I'm going to make is in some component of the metric.
Yes.
Which is some spatial component which
remains finite.
I could make it anywhere.
Yes.
Okay. So in terms of proper size of deviation of the metric from the background metric, it's always the same.
Yes.
So now.
And if I understand correctly, sigma ENS is a calculation you could do in the black hole background of computing the 2-point function of that spatial component of the metric. And in general, it's finite all the way up to L equal to infinity, because that sigma ENS is just a question of fluctuations in the black hole background, which are always small.
I guess my question is.
So I think sigma ENS is small, and this deviation that you're talking about is order 1. This deviation of this from the background would be order 1, because it's a wiggle you can measure in some component of the metric.
Right. I think that what I'm asking though is that if I make it different points up and down the throat,
Yes.
it's very redshifted.
It's very redshifted.
If I make the perturbation way down at the bottom of
Yes.
the throat,
Yes.
then from the point of view of the dynamics of the
Yes.
theory, it's a very small perturbation
Yes, yes, yes.
Of the thing I started from.
Yes.
Whereas if I make it up here,
Yes.
it's a very large perturbation.
Yes, I understand the question, but the reason we made this argument was precisely to get around this. You see, if you only look at asymptotic observables, then these observables down at the throat are very hard to discern. But if you grant me the fact that the metric itself is a good observable, then these observables also get disallowed in typical elements of the basis. It's true that asymptotically, if you're just measuring observations here,
Disallowed by what?
disallowed by this theorem, by the fact that you know such a basis element which had a wiggle down at the throat is one where this quantity remains finite. You know, if V is this basis element and A is this metric, then VAV minus the mean value, which is computed in the black hole, divided by the value in the black hole is order 1, and I'll claim that only 1 by S of basis elements can have such a wiggle.
So can you use this kind of argument to place a bound on how many geometric microstates there are?
I think you can use it to place a bound on how much the how large the wiggles can be. So the wiggles have to be order 1 over S or 1 over square root S.
But in what units? The units, I mean, are you looking?
This is a question of looking at the wiggle and dividing it by the order 1 over square root S in the the wiggle size of the metric, the size of the fluctuation in the metric is 1 over square root S into the metric itself.
So for the extremal black hole, I think there's clearly, I mean, this situation can clearly be improved. I mean, this discussion, because the extremal black hole has a throat which is at an infinite distance.
Yes.
The distance between the fuzzballs and the black hole solution is actually infinite. If you look in
the distance between the, I beg your pardon?
The distance between the horizon, because the horizon is at there's an infinite throat.
But remember, I was measuring distance by using units of this kind. So this distance is probably not infinite. This distance is L Planck, right?
No, it is infinite.
Well,
the extremal solution is infinite.
But I'm measuring distance. The words I was using to measure distance was looking at the size of the transverse direction, looking at the size of the
S2 is
S2.
going to be the same. So the size of the S2 is going to be.
But isn't it slightly different? The size of the S2 varies, right? And it's not exactly constant. So I would think that at the point where the throat caps off in the extremal fuzzballs, the size of the S2 is this. In fact, it is this. In the solutions that you found, this is the parameter A. So in the solutions where the
S2 has nothing to do. The size of the S2. The size of the S2 has nothing to do with A. The size of the S2.
At the bottom of the throat,
the size of the S2 starts to change, but it's not.
But isn't that at the point at which the size of the S2 starts to change? At that point, isn't it RH plus A squared? Shouldn't I think of it as that?
No. RH is infinity. The horizon is at minus infinity.
Well,
the
RH is
an infinite throat.
The throat is infinite, but I'm looking at the size of the S2. What is the size of the S2 at which the fuzzball starts to deviate from the black hole?
The size of the S2 is always n1 and 5, square root of n1 and 5.
But it's that's the size of the S2.
Given by the black hole. That's regardless of the depth.
But that size varies and hits a certain constant.
No. That's only for 2 charge. In 3 charge, the size stays constant.
It's exactly constant.
And then at some point, if you go
Okay, good.
like a parametric distance down the throat, then it starts changing. But the throat is.
So you're saying that here the size is just exactly constant.
Yes.
Okay, fine. Okay.
So the point is again, if
so the thing I'm going to ask you is, so you have to tell me what the black hole is good for computing averages of. Okay. So the reason I put in this L Planck was basically to say that once you're down a certain depth down the throat, then you might choose to say that the black hole is not good for computing averages. Okay. So you have to tell me at what depth are you going to say that the black hole is not good for computing averages. Up to that depth, whatever that depth is, you cannot have wiggles. You cannot have wiggles in typical states. So this L Planck was just put in to give you a measure, just to say that I'm restricting myself by saying that I'm going to trust my computation of sigma E and S.
Give me a length where the black hole should be a good approximation.
That's right.
And then your argument is that whatever the length of the black hole should be a good approximation for.
That's right.
At that length.
You cannot have large wiggles.
You cannot have large wiggles.
That's right.
So you're saying so if I'm to interpret it the other way, let's suppose for external black holes I find all the microstates where
yes.
go 5 years more. I find everything, we find all the superstrata and so on.
Yes.
And then you'd be basically saying that the external black hole has to stop describing the geometry at a scale which is parametrically larger than the place where the fuzz was different from each other.
That's right. And then you'll also have to tell me, some other things. You'll have to, if that scale that you're talking about is some scale that doesn't involve L Planck or doesn't involve a redshift of order 1 over S, then you'll have to tell me, you know, why the Euclidean saddle point, for example, is not good. You know, if you tell me that the extremal black hole stops describing.
The Euclidean is not good anyway. So I mean, for the extremal black hole, the Euclidean, you know, it's a zero temperature.
Right.
So the Euclidean picture is not worth any money anyway. So I mean, I think the meat of the argument here is about non-extremal. I mean, for extremal again, you can. I mean, there are people who claim that okay, the extremal horizon is a sky. There are people who claim that you know.
Well, certainly for non-extremal black holes, certainly for non-extremal black holes, you'll have this. But it seems to be even for extremal black holes, you'll have to tell me, you know, why the saddle point that. Well, it's not. I mean, it's true that there's some. It's a zero temperature setup, but you'll have to. Let's see. Okay, but okay, but it's a zero temperature setup. But you know, there's still some good calculation I can do. Why is it that saddle point is not?
It's a little bit delicate, right? There are third law type issues.
There are third law type issues, but that doesn't affect the fact that, you know, I can do a reliable. So I still don't see why that. You know, if you like, I'll, yes.
The calculation which Nick Warner did with his students. So if you look at the microstate, which the difference from the black hole at some distance a. And you look at an incoming geodesic, and you can ask at what point the incoming geodesic starts in the microstate starts experiencing a strong force, a strong tidal force. And you think because the microstate differs from the black hole in size A, then you know the incoming geodesic is going to be very happy to feel the same as the black hole geometry until it hits A. But actually the answer is that this is not the case. If you look at the incoming geodesic, the incoming geodesic starts experiencing a large tidal force at a distance which is square root of A times B in our language. So B is the size of the momentum, and
but B is order 1 in your language.
Sorry?
I tend to think of B as order 1.
B is the momentum.
So B
is the momentum.
So these are these parameters in your these. Yeah. So I tend to think of B as being the ADS scale. Mm-hmm. So let's think of B as order 1, in which case you're just, you know, it's just square root A. That's good.
But
you know, but can I say
there, for example, the geodesic differs from. So there you can say that you cannot trust the black hole solution.
Okay, so
the black hole solution will not give me good physics.
So
even at
so we can come to that later. But at some point you'll have, you know, this theorem applies as long as the black hole solution gives you good physics, and you have to tell me where the black hole solution gives you good physics still.
I can flip it over and I can say if I have the microstates, then I can claim that the black hole solution doesn't give me.
Yes, but then you have to make sure you don't run into contradictions with various other arguments about the black hole solution. You know, because for example, in two-dimensional there are many calculations you can do in the thermal state, and you have to make sure that you don't run into trouble with other CFT calculations. And the moment you start saying that the black hole solution does not even describe averages, you'll have to do two things. First, you'll have to tell me what the average geometry is, because there is some average geometry which is the hard typical geometry. So you'll have to correct the black hole. So, you know, if the black hole solution stops giving you good physics here, there'll have to be some average geometry which will correct the black hole geometry somewhere here. You'll have to tell me what that average geometry is, and you'll have to make sure that calculations in this average geometry do match CFT calculations. So you know, there's some but that's something which you'll have to tell me. Yeah.
Yes, I had a question about the observables that you're using. So
yes.
You said that you're happy to use static some arbitrary point on the throat and maybe consider some sort of extremal. But sorry, I mean that can maybe be mapped to. So suppose that I only want to talk about boundary observables. So I guess this you using the bulk two-point function, for example, down the throat.
Yes.
This can sort of be mapped to a boundary two-point function, but it can go to arbitrary.
No, that's very hard, because you know, getting the 1-point function of the bulk metric, as you were just discussing from the boundary, is not so easy. There isn't even a good HKLL map for that. You know, because the map is between, you know, so looking at. So getting the 1-point function of the metric, as far as I know, you really need to have a bulk observable. To get that from a boundary observable is much harder. In fact, I'm going to say something more about boundary observables in a minute.
But what I was going to ask is, I mean, doesn't the fact that you want to use bulk observables deep down the throat equivalent to using boundary observables for very long times?
I don't think so.
Case in which you might run into these issues with e to the s times.
They'll have to be exponentially. So you know, can I say if you use the fact that they're not exponentially large is already clear, because the metric at this point in the throat is bounded. So the only thing I need to worry about in applying my theorems is the fact that the sigma ENS doesn't become too large, and it doesn't become too large. You know, so even if you map it to some boundary observable, that's a boundary observable which has bounded fluctuations, because the metric at this point in the throat is bounded. the observables for which these kinds of theorems run into trouble are unbounded observables, so observables which where the fluctuations become very large.
The method down the throat is some sort of very special result observables.
I think you should really think of the metric down the throat as being the metric down the throat. I think if you think of it as a separated boundary observable, first of all, I don't know how to make that precise. If I give you 2-point functions in a boundary, to reconstruct from that the 1-point function of the metric, I don't know how to do that. The HKLL prescription doesn't tell you how to do that. But secondly, whatever it is, you should just view the metric as an observable in its own right, and you can check, you can estimate the fluctuations of the observable, and the fluctuations are bounded. So it's not one of these observables that has problems with this theorem.
Right, but it's more of a bulk than a bounded observable.
It is a bulk observable, yes. It's very explicitly a bulk observable. But that's fine. The bulk observables are good observables, right? There's no,
but I'm just saying it's not obvious what happens when I rewrite them in terms of boundary observables. Suppose that I could do something
Yes.
of HKLL for it.
But whatever it is, we'll still have
It
to.
would be obvious that the fluctuations.
Well, it would be, because if you rewrite it correctly, you better be getting the right bulk answers. So
I'm just saying.
yeah. Okay, good. Sorry, I went fast. Okay, good. So this is the discussion we just had. So the statement is, even if fuzzballs form an atypical basis, almost all fuzzball states must have metric expectation values that are within order 1 by square root s of the black hole metric. Let me modify the last line in light of the discussion we had. Except when we are Planck length away from the horizon, this can be modified with except when the black hole stops giving a good description of average physics. And Yusuf is going to you have to tell me when the black hole stops giving an average description of black hole physics. So I was assuming that the black hole stops giving you a good description of average physics once you're within Planck length. But everywhere I have this figure, you should change this to whenever. Whatever the claim for when the black hole stops giving me an average description of good physics is, and you have to remember that when that claim is made, it has to be consistent with many other checks, because the moment you say you have a different geometry for the average, that's a strong statement, because then you can compute thermal averages and compare it with that. You can do Euclidean calculations. There are many calculations one can do.
There's another way to solve this problem by actually having the black hole geometry to be a good description all the way to the fuzzball structure, but making the fuzzball structure to be made of very small bubbles.
That's something of this kind. That's some picture of this kind.
Yes, but if the bubbles are size 1 over n
yes.
in ADS units, but
yes.
they're size 1 in
yes. So I'm going to.
So the bubbles have 1 unit of flux each, for example. Then I can also get that from.
Yes. Yes. So that's literally this picture, right? Where these structures are Planck length structures. Mm-hmm. Is okay.
So
yes.
I still want to understand
yes.
the previous transparency, whether this estimate is powerful or
yes.
or not.
Yes, please.
Maybe I want the one before. Yeah. So there is already a large catalog of fuzzball solutions.
Yes.
There are estimates that you can get e to the q to the 5/4
okay.
states in some way. So if I tried to pick a basis where I have e to the q to the 5/4 states that Yosef and his friends can describe, and I
that doesn't actually run into contradictions.
So there are lots of states that I from that ensemble that I can choose to be basis elements.
Yes.
So if I do that, where does that lie? So
that doesn't actually run into contradiction,
and so on and so forth.
So if it's a set which is exponentially suppressed, if it's much smaller than e to the s, and first of all, that's not in contradiction with this. This is a power law statement. So this is a statement that almost all of your basis elements to within the power law have to look close to the black hole metric. But what you're mentioning is an exponentially small set. The set of solutions you're talking about is not e to the s. It's e to the s to some power, to some smaller power, right? It's e to the s to the 4/5 or something. So that's an exponentially small subset. So about the exponentially small subset, there's anyway nothing I can say, because you can always have an exponentially small subset of elements and they can do whatever they like, and statistical mechanics can say very little about them. So the question I want to ask is about typical states, because I still want to understand the question of what happens to an observer as he falls into a typical state. And if there's an exponentially small subset of states that are doing something else, there's nothing I can say about them. And that's perfectly allowed.
So I think it's possible to make a argument clear. If you force a U1 invariance, then we are computing. So for example, if you look at this b to the to the 5/4, I think if you force a U1 invariant on the
yes.
on the system, they are going to be all the states.
Or going to be all the states?
Yes.
Ah, good, very good. So then,
I think it may be possible. We haven't shown it.
very good. So if you
our
can,
states have-
if you do
so
that,
these exponential suppressed guys, they are basically
Very good.
psi dependent but V independent. So if you force a Johann invariance on V, essentially you can get all these.
very good. So then all of these theorems apply, and then one can compute the mean geometry, for example. One can ask how well the black hole. So then you can answer these questions for this. So we can discuss this more. But first of all, you can compute in those states what the average geometry is, because you can. I'll show you. We did for the two chart solutions. We computed what the average geometry is. You can compute what the average geometry is. You can start where it starts deviating from the black hole. You can check if that's consistent with other expectations, and then all of these theorems should apply. If there's any, so this doesn't have to be microcanonical. If there's any symmetry you can impose or any charges you can impose so that the set of solutions you have span the full set, then you can immediately start applying these theorems.
Excellent.
So then we can okay.
Okay, thanks.
Okay, good. Okay, good.
It's like a seminar, so don't feel bad, don't feel rushed.
No, I'm fine. As long as you guys have patience, I'm happy. I'm happy. Yeah. No problem. Yeah. If you get bored, you should tell me. Okay. Let me say a little bit about eigenstate thermalization. Okay. This is a statement about boundary observables. So people were asking. So there's a statement which is called the eigenstate thermalization hypothesis that says if you take a basis of energy eigenstates, but really it applies to almost any basis you pick. And you measure the expectation value of some observable in energy eigenstates, or in some other elements of the basis that are not correlated with eigenstates of A itself, then the eigenstate thermalization hypothesis states that these matrix elements are given by some smooth function of the energy of this guy times delta ij. So that's the overlap, that's the matrix element that takes Vi back to Vi, plus some random phases which have a typical magnitude of e to the minus s by 2. Okay? And eigenstate thermalization is the statement that these Rij's are some random phases which tend to average out to 0. Okay? Now, if you impose eigenstate thermalization, then this says that fuzzball states should resemble black holes closely, even for operators where sigma ENS is not small. Now, what are operators for which sigma ENS is not small? These operators, for example, are 2-point asymptotic boundary functions. Okay? So if you computed, for example, on the boundary, O omega dagger O omega, where this was the mode of some field, then you know that in the thermal state, this is something which will give you e to the minus beta omega by. Okay. Now you can check that if this is an observable, then the fluctuations of this observable in the thermal state are as large as this classical expectation value. Okay. So if this is my observable A, and fluctuations of A are as large as my classical expectation value. So the previous result I told you is not strong enough to say that in typical basis elements, this should take on this value. But if you assume eigenstate thermalization, and indeed people do believe that eigenstate thermalization holds for CFTs that have holographic duals, then you could argue that even quantum operators of this kind, states which are measuring, operators which are measuring the quantum states of the field, should take on the same value in typical basis elements as they do in the black hole. Okay? So if you assume eigenstate thermalization, then this says that not only the geometry, not only 1-point functions of the metric, but also the quantum state of the fields, which is measured by 2-point functions, okay, has to be the same in typical fuzzballs as it is in the black hole. Okay? Now in this talk, I'm not going to assume the eigenstate thermalization hypothesis, although I think it's important to keep in mind that if we do assume the ETH, then in fact you can argue that even 2-point functions which measure the quantum state of the field have to be the same in typical fuzzballs as they are in the black hole. Okay?
So by quantum state, you just mean fluctuations around the mean? I
mean fluctuations about the mean. So even you see fluctuations about the mean, if you look at the fluctuations of the fluctuations, those are the same size as the fluctuations. So if you looked at 4-point functions, those would be the same size as this. So the previous theorem is not enough to constrain, say that these matrix elements should be the same in typical basis elements as they are in the thermal ensemble. But if you assume eigenstate thermalization, then that is enough. Okay. Okay. Now let me say.
Lundi, mardi, mercredi, jeudi, vendredi, samedi, dimanche, fin d'essai.
Okay. Assuming that wasn't something to say. Yeah, good. So now let me say something about the energy gap. Okay. So now we have. By the way, I'm realizing I'm going a little slow, but I think we'll go faster as we come to the technical parts. So let me say something about the energy gap, which is a separate argument. That constrains fuzzballs. You see, in a typical statistical mechanics system, if you take some finite band of energy states between some large energy E0 minus delta and E0 plus delta, then there are e to the s states in this band. Okay? Now that means that if there are no degeneracies, and this is an important point, if there are no degeneracies, then the gap between neighboring energy eigenstates is e to the minus s. Okay. The second thing is that this gap can actually be detected. This is not just an abstract gap that exists between neighboring energy eigenstates. If you take one energy eigenstate and you hit it with an operator, then you excite all of these neighboring energy eigenstates. Okay. So in the dual geometry in an ADS-CFT setup, you can see the fact that there are a whole number of energy eigenstates which are close to your initial energy by just perturbing the geometry with a massive particle. Okay. So if you really have e to the s states around the state that you are in, and you perturb the geometry with something which has an IR cutoff, so that's why I said massive particle, then you will see the fact that you have all of these, these very small degeneracies in energy, these very small gaps in energy. Okay. In particular, this will be manifested in a continuous spectrum in Fourier space of the 2-point function of A, if you were to measure it. Okay. Now there is, I want to point out that there are some theories where the gap is much larger. So for example, if you have a free theory where energy eigenstates are degenerate, then indeed the gap could be much larger. So for example, if you look at the symmetric product orbifold, then that has a much larger gap. The gap is order 1 over s, or in this language I'm using. And that gap is much larger, and the reason it can be so is because of degeneracies. Okay. But if you're not in a free theory, even if you're in an integrable theory, then the gap between energy eigenstates is exponentially small. Okay. And this is a much stronger expectation than eigenstate thermalization. So I said previously, I'm not assuming eigenstate thermalization, but the fact that the gap between neighboring energy eigenstates is e to the minus s is really something that holds almost in all non-free statistical systems. In fact, before this discussion of quantum chaos, by looking at these out of time order correlators came about, the way statistical mechanics people used to distinguish between systems that were chaotic and non-chaotic was by looking at the statistics of energy eigenstate levels, and the statistics in both integrable and chaotic systems was that the gaps were e to the minus s, but then people could argue about how those e to the minus s gaps were distributed. Okay. But the fact that there is this exponentially small gap is true even if you're in an integrable system, and this is something that you do see in black holes. Okay. You see it in black holes because black holes allow a continuous spectrum because of the horizon. It's the horizon that allows you to have, that suggests that you have this very small gap between excitations, because the horizon allows you to have a continuous spectrum the moment you try and excite it. Okay. And this is a feature of the black hole geometry because of what I said. It's not a bug. It's not something that argues against the black hole geometry, but it says it's a feature of the black hole geometry because it suggests the black hole is dual to a statistical system that has e to the s states around it. Okay. And this is an independent argument that the fuzzball metric must almost have a horizon, because if it doesn't almost have a horizon, then it won't give you this kind of a continuous spectrum. Okay.
I think there's again a discussion
yes.
before. I mean,
yes.
we discussed for about an hour, so maybe
yes.
we shouldn't discuss again.
Okay.
I think there's again the problem of on top of one particular state. Which is
this is on top of one particular state.
You can build the whole tower, but then the question is, can you go from one tower to the other one?
Yes.
Can you excite the whole?
I think in typical statistical systems you can. You see, so just to get it, you see, it could be that you have some energy eigenstate here, and then there's some other energy eigenstate with EI plus e to the minus s, and maybe another guy here with EI plus e to the twice minus s. But when you hit this guy with an operator, you don't excite any of these guys, but you excite somebody who is at EI plus 1 over s. So when you hit this eigenstate with an operator, you just skip all of these energy eigenstates and you straight away go to some higher level of this kind, and the same for these guys. So you have a whole bunch of decoupled towers which are not talking to each other. So this is possible, but as far as I know, it would be extremely special, and this is something which doesn't usually occur in statistical systems.
Property of any glassy system.
This is a property
Of any glassy system.
which is what that.
Where you have exponentially many states that are near to the ground state, but they
yes.
don't talk to each other.
You have exponentially many states that are near to the ground state, but they don't talk to each other, but this is not so you that could certainly be that there are many states, but is it also the state but in the system there are also yes.
Thermodynamics is very different, but it's also true in systems that have localization, right? So where you have any system you can create where the phase space divides up into pockets that don't talk to each other.
Yes.
So you can have thermalization within a
Yes.
pocket.
Yes.
Okay. But different pockets talk
Very
to
good.
each other only weakly.
Very good.
Okay. So spin glasses are like that. Systems
That's
that
right.
have Anderson localization
That's right.
are like
That's
that.
right. Good.
And so,
but-
so if I have enough pockets, I can have gaps in the total system
Yes.
that are very tiny, but you know, statements about thermalization.
Yes, it's possible, but let me say even there, the typical state would be a wave function which has support on all these parts of phase space. The wave function would spread out, and so a typical state would still not, would still not have this property. That, but it's true that there are some atypical states where the wave function is concentrated on one pocket of phase space, and those pockets may not talk to each
I
other.
think this is confusion about hard typical states and what you measure and what you have in the.
It's true that in this kind of system you're mentioning, you might be able to find a basis of states which have this property. But can I say even in these systems, you have a pocket of states. I would suspect that this pocket of states itself has, an e to the s divided by some number set of states. So the fact that the gap here is, it could be that this gap here was e to the minus s by n. I suggest I think what you're saying is that in these systems it goes up by e to the minus s divided by some number n, where n is a number of pockets of phase space. So I don't think this number becomes e to the s.
I'm not saying this is a way of getting around some of your arguments. I'm just saying that
Yes.
one should be a little bit careful about making statements about typical states.
No, but I think your point is well taken. But I think that it would suggest that maybe n into e, yes, that the typical gap would be some number of pockets of phase space into e to the minus s. So you skip over many other pockets of phase space, but in each pocket of phase space, I suspect you have almost e to the s states. But here you would have to take n itself to be exponentially large. So you'd have to have exponentially large number of pockets of phase space. So that would be very unusual, I think. Okay. So this is another argument that fuzzballs have to have this structure. Once again, let me, in light of our discussion, this doesn't have to be RH plus L Planck, but whatever point the black hole geometry stops giving you a good description. So now the question I want to ask is, can you use classical solutions, which is really what we have at hand in the fuzzball picture, to argue for such a structure. Okay? So we've argued that just general statistical mechanics considerations tell you that you must have such a structure for typical states. Now I want to ask, are classical solutions powerful enough to argue that such a structure does exist? Okay, so now here are some diagnostics of this. Let this O hat of R be some bulk observable. So far I was talking about this observable A, which was some boundary observable, but now I'm going to use O hat of R exclusively for some bulk observable. And let OBH be its expectation value in the conventional geometry. And let there be some fuzzball state which I'll call F, and I'll say the expectation value of F in this fuzzball state is O fuzz. And then I can define the fluctuations of this operator in the fuzzball state. This is different from the ensemble fluctuations I was talking about. These are the fluctuations of this operator in the fuzzball state itself, and I'll call them sigma. Okay. Then I can define two parameters. One for lack of imagination, I call the quantumness parameter. Okay. Which is roughly a measure of the size of the fluctuations divided by the expectation value, and the other I call the difference parameter, which is a measure of how much the expectation in the black hole differs from the expectation in the fuzzball. Okay. Now the
R is the statement that you're making this perturbation some particular radius down the throat.
Yes. So R is a sign that it's localized at some point. It's a bulk observable. Yes, it's a bulk observable. I'll give you concrete examples in a minute. Okay. But for now. So here are two parameters I can define. Now, what do these two parameters measure? What's the significance of these parameters? The significance of these parameters is as follows. This parameter Q tells you how reliable a classical solution is. You see, if the square of the expectation value is not the same as the expectation value of a square, then you should really not be using classical equations of motion to analyze this system, okay, to solve this system. And so if you want the classical solution to be reliable, then it better be the case that in the coherent state you constructed, or in the solution you constructed, QO be parametrically small. Okay. On the other hand, if you want your solution to be interesting, to be distinguishable from the black hole, then it better be the case that DO be large. Okay. Okay, so if you want your solution to be interesting, then DO should be large, and if you want it to be reliable, then QO should be small. Okay. Now, I'm going to argue that in fact, if you have a structure of this kind, then you run into the following trouble. You run into trouble because far away, when you're far away from this point where the black hole is giving you a good description, where the black hole stops giving you a good description, in this point this parameter d, should have been do, d is very small. Okay, d is close to 0 because all the observables that you have are the same as the observables in the black hole. Okay, so in this region d is small, and q is also small. Q is small because the solution is reliable. The moment you come to this region where the black hole stops giving you a good description, then d becomes large, but quantum fluctuations also become large. Now the argument, I haven't given you yet a watertight argument for why quantum fluctuations become large, but the argument is simple. The argument is simply the fact that once you come to some region where the throat has become very large, where you're deep at the bottom of the throat, or once you're for non-extremal black hole, once you're L Planck away from the horizon, if you have a solution, if you have a solution, classical solution, we have explicitly inserted a length scale which is of order L Planck, then there are fluctuations in that length scale. Okay, these fluctuations, for example, come from the fact that in quantum gravity you just can't pin down a Planck scale length scale absolutely precisely. And if you have such fluctuations, then you would expect that the size of the fluctuations is the same order as these classical expectation values. Okay, so this is at this point just an expectation which I'm going to verify in some examples, but the expectation is that if you have Planckian structures, or if you have these very long throats, then when you have these very long throats, you have fluctuations in the lengths of the throats, and you run into a situation where the fluctuation in the length of the throat means that quantum fluctuations are as large as your classical expectation values of quantities like the metric. Okay. So the picture that it suggests is that first of all, statistical mechanics arguments tell you that you have to have a structure of this kind, but if you have a structure of this kind, then you can't analyze it using classical solutions, because the classical solutions have the property that they are either uninteresting in this region, and in the region where they are interesting, they are unreliable because quantum fluctuations become large. Okay, so this is a summary of the first part that I said. I said that just from general statistical considerations suggests that fuzzballs can only have Planck scale structure. We had some discussion that maybe fuzzballs can have larger structure, which I think needs to be checked against many things. But if this is the case, then this suggests that solutions are either indistinguishable from the black hole in most of space. In most space they look exactly like the black hole, or in the part where they are distinguishable from the black hole, they are unreliable. Okay, so this is a summary of what I said so far. What I'm going to do now is try and verify these conclusions in some examples. Okay, so I hope this part will now go a little faster. So now I'm going to verify these expectations I had in two setups. One of them is the original Lunen-Mathur two-charge solutions that were found, I think, in 2000, many years ago, which really, I think, if I'm not wrong, started off the whole fuzzball story by finding these solutions. And then I'll look at these most recently discovered multi-charge solutions that were found by Benna and many others, partly here. Okay, so let me start by a discussion of these Lunen-Mathur two-charge solutions. Okay, so these are the solutions which all of you know much better than I do. So there's a metric. The metric is controlled by some profile function which is given by this f of s. These solutions are claimed to be dual to the Ramond ground states of the D1, D5 CFT. They're supported, there's the metric in the string frame, there's some dilaton. The metric is supported by some fluxes. The fluxes are controlled by these forms. I'm going to define some auxiliary quantity which I'll call Wi, which looks very much like this one form except it doesn't have a prime on the s. I'll explain in a second why this is an interesting quantity, but for now it's just some auxiliary quantity that doesn't actually enter the metric. Okay. So all of you know this, so I don't need to spend much time on these solutions. Now the conventional solution, which is the solution which is just obtained by setting this profile function to 0, in which these harmonic functions f1 and f5 that appeared previously just become this. Okay, this profile function vanishes, and the metric just becomes this, with the f1 being this and f5 being this. Okay. Now the conventional solution actually has a vanishing horizon, and because it has a vanishing horizon, it's slightly different from the macroscopic black holes that I was assuming tacitly till now. In particular, this conventional solution, because it has a vanishing horizon, also becomes unreliable at the point r equal to 0. Okay. So this conventional solution also becomes unreliable at the point where x squared goes to 0. And so it's a slightly different setting, but we will see nevertheless that this system has many of the properties that we expected it to have. Okay, so now Slava Rychkov quantized this system This is it's a simple enough system that he was able to perform this quantization, which leads to a very nice and intuitive result. The intuitive result is that this profile function that appeared previously gets promoted to an operator. So you just write it as an infinite sum of creation and annihilation operators, and the states that correspond to these two charge states that we are interested in are states where the Hamiltonian in this set of harmonic oscillators is just given by n1, n5. Okay. There are some other parameters in this system which are here. They are not of any particular interest. I mean, they are not of any interest for. They are interested if you follow the details, but you don't need to look at all of them right now. The other interesting thing is that Rychkov was also able to count the entropy of solutions in this harmonic oscillator system that obey this constraint, and he found that the entropy was 2 pi into 2 by 3 of square root n1 n5. In fact, more recently, a couple of years ago, Chetan Krishnan and Avinash Raju also found that if they look at excitations on a compact manifold, they quantize the system on K3, they can actually reproduce the full entropy, which is 2 pi into square root of twice n1 n5. Okay, but we are not going to look at these excitations on this compact manifold. We'll just look at original setting explored by Rychkov, in which the entropy is large, not the full entropy, but it's large enough. Okay, so now what are we going to calculate? You see, because we have a quantum setup, we would really like to calculate the expectation values of the metric. That's too hard for us. So what we'll calculate are expectation values of these harmonic functions, f5, f1, this one form that appeared in this auxiliary one form, and we'll also compute fluctuations by computing f5 squared, f1 squared, and also fluctuations in this one form. These fluctuations are not interesting because this expectation is already 0. Okay. Now, in fact, I'm going to make another technical simplification. We'd really like to compute expectations of these guys in the microcanonical ensemble, but it's technically easier to compute expectations in what you can call the canonical ensemble. Of course, this system doesn't really have any temperature, but you can nevertheless compute trace of e to the minus beta h, where beta is said to be the inverse temperature at which the energy of the set of harmonic oscillators becomes n1, n5. Okay. So the expectation values computed in this are just easier to compute technically, and they give you a very good approximation to these microcanonical ensemble, to these microcanonical expectation values up to terms that are suppressed by 1 over square root n1, n5, and that's good enough accuracy for us. Yeah.
Excuse me. So this is in a vacuum, which is defined by all annihilation operators in F.
That's correct.
But what is geometrical interpretation of this? Is there any?
So the geometrical interpretation of the states that you're looking at are only states which have h is equal to n1, n5. The vacuum is states which have h equal to 0. So that's not an interesting solution. Okay, so n1, n5 is given by the energy. So in this harmonic oscillator.
I would expect some classical states or classical solutions to be some sort of coherent states rather than just a bunch of creation operator acting on vacuum, right?
So the claim, very good. So it's in this harmonic oscillator system, you could of course construct coherent states of f of s. You could construct states where where f of s has so f of s, you can't construct eigenstates of f of s, but you could think in this energy space which has h is equal to n1, n5. You could construct superpositions of these states so that f of s is almost an eigenstate, which would be the coherent states you're looking for. So in this to go from this quantum state back to the classical solutions, you need to find the right superpositions where f of s has a narrow spread. That's a good question, actually. Yes.
Yeah, it's a question of whether the wiggles on the geometry are string scale or ADS scale. If you want a nice big coherent state where you've got a macroscopic number of the same kind of oscillator excited, then you're building something which has got features that are of order the ADS scale. Whereas if you are looking at some typical thermal state, then the features are all the string scale.
Okay. Maybe even smaller, but maybe let me say a little bit more and we can come back to this discussion. Yeah. Okay. So in any case, there's some well-defined calculation one can do computing these expectation values. So here's the answers. So I won't go through the details of the calculation. These are the answers. We computed the expectation value of f5 minus 1. It turns out to be q5 into 1 minus e to the minus r square by tau, where tau is given in terms of these parameters I described previously. I'll tell you what the physical meaning of tau is. This is f1 minus 1. This is this one form turns out to be 0 even in the quantum setup. That's why it's not so interesting. This one form, which would have been 0 in the classical setup, turns out to have some interesting expectation value, and that's why we chose to to look at it. Okay, so these are the quantum expectation values that we found. Some of these calculations were also done many years ago by Yandeep Bohr, Vijay Balasubramaniam, Cheryl Shok, and one author more I'm forgetting. Oh, yes, that's right. So they also computed some of these 1-point functions. So the interesting thing about them is that these if you substitute these quantum 1-point functions back into the metric, you get this some average geometry, which is the average geometry we were discussing earlier. And this average geometry differs from the conventional geometry, as you can see from these expressions, at the point when r square is equal to tau. Okay? Now, what is the point at which r square is equal to tau? What is the physical meaning of this point? One way to physically measure what happens when r square is equal to tau is to measure the radius, the physical radius of the compact direction at the point when r square is equal to tau. If you measure the physical radius of the compact direction at the point when r square is equal to tau in units where string length is set to 1, you find that this physical radius is given by the following. It's given by some L Planck to the 4 divided by the square root of the compact manifold in string units in the string frame times some units times some factors. Okay. Now, if you want for the solution to be reliable, you better be in a setup where the volume of the compact manifold in the string frame is larger than 1. Otherwise, you should T-dualize to the frame in which the volume of the string of the compact manifold is larger than 1. Second, you don't want the dilaton to blow up, and that tells you that this Q1 by Q5 is order 1, and that tells you the point at which this average geometry starts differing from the conventional geometry is a point where this stretched horizon, or the size of the compact dimension, is much smaller than the 10-dimensional Planck scale, okay, which verifies the picture that we had previously. So this quantum corrected geometry starts deviating from the average geometry, from the conventional geometry, once the compact direction has shrunk much below the Planck scale. But well before that, the geometry stopped being reliable, because you should have, once the compact dimension became smaller than string scale, you should have T-dualized to another frame where the compact dimension was not smaller than string scale. Okay. So well before the compact direction reached this size, the solution became unreliable. But indeed, this quantum corrected geometry corrects the conventional geometry only at this Planck scale, which verifies the picture I showed you previously. Okay, that the average geometry you get from fuzzball seems to correct the conventional geometry at the Planck scale. But in fact, so this is what I just said. Away from r square equal to tau, just looking back at these expressions, this quantum geometry is indistinguishable from the conventional geometry because of this exponential factor. But at r square equal to tau, the geometry looks like it's differing. But because this point is the point where the compact direction has become Planck scale, you expect that the geometry is unreliable, because you expect quantum fluctuations will be large. Okay. In fact, in the system, we can actually compute quantum fluctuations. So we can compute quantum fluctuations, which we did because the system has been quantized. So we computed quantum fluctuations. You get some horrible expression. Here are the quantum fluctuations in this F5. So you get some expression. The final integral actually has to be done numerically. You get some exponential integral functions. You don't need to look at this expression. This is just to say we did the calculation. I'll parse this expression for you in a minute. And then now for this F5 function, since we have computed the fluctuations, I can compute what this difference parameter and this quantumness parameters. Okay. Remember, I had defined for you these difference and quantumness parameters, which looks at the size of the quantum fluctuations divided by the classical expectation values, and this looks at the deviation from the black hole. Okay. And you can compute these parameters. These parameters are functions of r. They're functions of where you are, okay, because F5 is a function of r. And here is what these fluctuations look like near r square equal to 0. Okay. Near r square equal to 0, the difference parameter blows up. The difference parameter blows up because F5 blows up at r square equal to 0. So it looks like the solution is very different from the black hole, but the quantumness parameter approaches some finite value, which is some 0.426. Okay. So this is the statement that the solution has large quantum fluctuations in the region where it looks interesting. In fact, you can plot both these parameters as a function of r square over tau. This plot you have to do numerically, and you see this completely verifies the expectation we had. If you're at large values of r square, so you're away from this point where the conventional horizon shrinks to 0, the solution is reliable because this q parameter, the quantumness parameter, goes to 0, but the solution is also not very interesting because it looks exactly the same as the conventional solution. Okay. The moment you start approaching close to r square equals tau, this quantum corrected geometry looks like it's interesting because this difference parameter in blue starts growing, but it also becomes unreliable at the same point because quantum fluctuations become order 1, they become as large as the classical expectation values. Okay? So as expected, the solution is either indistinguishable from the conventional solution, which is what happens in this region far away, or it's unreliable, which is what happens here. Okay? Now this you can look at for other quantities as well, not just for F5.
What precisely does unreliable mean?
Unreliable means
yes.
Yes.
To me, there are two senses of unreliable. Yes. One is that you can't trust classical intuition, and the other is you can't calculate anything. Things can be quantum, but you can still calculate.
Yes.
So
this solution.
Which
yes.
precisely do you?
So this solution is obtained by solving some Einstein's equations. But the moment you compute the Einstein tensor, this involves in particular products of the metric. But if products of the metric are not, expectation values of products of the metric are not given by products of expectation values, then you shouldn't be solving the classical Einstein equations to compute these solutions. So it's unreliable in the sense that if products of it's unreliable in the sense that if g mu nu squared is not equal to g mu nu squared, and you solve Einstein's equations to get a certain solution, that solution is not a good solution in a regime where this applies. So in particular, we take this solution, we can compute expectation values of squares of the metric, squares of components of the metric, squares of F5, and these expectation values differ very significantly.
Yeah, but I guess my question is,
so you shouldn't be solving.
Are you claiming that quantum gravity corrections are going to be huge in this geometry?
I think quantum gravity corrections in this region r square equal to 0 will be strong, yes. But at least I'm claiming that these.
is also blowing up, so that's expected.
That's expected.
When you make them very small,
that's expected. But
you
yes.
are making them dipole charges of order square root of n
Correct.
5, so then.
Correct. But I'm saying that the fuzzball solutions are not giving you an accurate picture of the physics near r equal to 0. If you need an accurate picture of the physics near r equal to 0, you need some more powerful techniques. These classical solutions are not giving an accurate picture of the physics near r equal to 0 because they are obtained by solving some Einstein's equations. And those Einstein's equations assume, that this left-hand side is equal to this, and that's just not true. You can, there's an internal inconsistency.
But there are many examples. For example, when you have a string solution, which you can describe using the Bonney-Infeld action. So this is very well-known. I mean, supertubes, for example, which give the Riemann geometries, they can also be described in the regime when by supergravity, whatever you call supergravity quantum corrections are huge, and you can describe using the Bonney-Infeld action. And so they have a perfectly good description using many languages. There's a supergravity language when G string times n is Markov bigger than 1. There's a Bonney-Infeld action of the D2 brane of governing the supertube in the regime of parameters where the dipole charge is small and the number of D0 branes is large. There's a matrix model description using D0 brane matrix model. So there are 3 descriptions. You're basically saying that one of these descriptions breaks down. And you go, but essentially, I know that there's another description. If I just
so what is that? I don't know what that other. Sorry, I don't know. So
supertubes, for example, which are the Riemann geometries.
Yes.
They were discovered by Matthäus and Townsend, long before Riemann.
Okay.
And they were discovered as using the Bonney-Infeld action of a D2 brane, which has F1 and D0 charge.
So the question I'm asking is, do these solutions give you an accurate picture of physics near r equal to 0?
So if you look at the supertube description is actually valid for way far away from the place where the supergravity description is valid, and the matrix model description of supertube, which is again a D0 brane description, is also valid in a different parameter regime.
So
the only thing you are saying here is that the supergravity regime, which you have here
yes.
for the 2-charge solutions,
yes.
is not valid anymore. But then I know that if I look at the supertube, for example, I don't know, with some shape, and I completely score its features, I can actually get exactly the same computations in the regime number 2, where the supertube is described by.
I'm sorry. I'm not understanding this thing at all.
What I'm saying is that your quantum fluctuations, that just because you have quantum fluctuations and your description is breaking down, doesn't.
When you have quantum fluctuations.
Let me ask a concrete question.
Yes.
I'm perfectly happy to accept your calculation
yes.
saying that there is some parameter which is getting large.
Yes.
So
the parameter is this one. Yeah.
Okay.
Yes.
But that's the curvature, right?
No, it's not the curvature.
Right.
Yes.
So I'm still fishing for what I should conclude from this, because would you say, for instance, that even in this regime, classical string theory is still reliable?
Now I think classical string theory has also stopped being reliable here. This is the regime, I think in the regime near r equal to 0, which is the regime where I think classical string theory is also not reliable. So I think if you wanted to understand, the only thing I would like to take away from this is that these solutions were obtained by solving Einstein's equations, and I think that that solution, the form of that solution ceases to be valid. So in particular, the question I'm trying to answer here is, so it's an interesting question to ask, what happens near r equal to 0 at the point where the conventional solution looks like it has a singularity because the horizon vanishes? And one answer might have been that you should actually think of these fuzzball solutions and think of this quantum corrected geometry which you get from the fuzzballs, and that actually caps off with some nice smooth geometry near r equal to 0, and that this is giving you an accurate picture of physics near r equal to 0. So the takeaway is that that's not the case. So if someone had asked you what happens near r equal to 0, and someone else had said, well, the answer is given by taking this quantum corrected fuzzball geometry, then what I'm saying is that that's not the case, because the quantum corrected fuzzball geometry has quantum fluctuations which are as large as a classical expectation
value. Look on the previous slide. I think
yes.
Emin's answer is actually, I think Emin is right. No, sorry, on the previous one. It's the one about, yeah, there.
This one.
The R stretched.
Yes.
So there clearly I can make the, if you look at supergravity, indeed, you need your torus to be bigger than 1 and so on and so forth. But
yes.
if you look at the full string theory, for example, the kind of solution which Emil and Stefan are looking at, then in the full string theory, I can get a solution. I can get super tubes described in the full string theory, which are like way.
So
which are what?
Precisely. The reason I asked the question is that we now have known for a year how to construct the sort of simplest round super tubes that Luna and Mathur described as exact classical solutions in string theory. Okay. So there it's presented to you not as some metric geometry. The metric geometry is some kind of sigma model approximation to what's going on, but
yes.
there's an infinite list of correlation functions
yes.
that can be
yes.
principal computed exactly.
Yes.
So this sort of a diagnostic of what's going on, it may be true, but
I think
it's
this
not an indicator that classical string theory is breaking down.
Well, I think this would also apply in classical string theory, because this is just a question of whether any classical solutions are valid. So I would claim that if you looked at these super tubes and you looked at the regime where these tubes were much larger than this size. So this size, this tau is roughly, this parameter tau is roughly controlled by the size. It's controlled by integral of fs squared. This profile.
Again, I think this is very simple. This v of the compact duration, you can then take it to be 10 to the power minus 100. And your string theory is still okay. So the v of the compact dimension.
Well,
v
yes.
of the compact dimension, I can take it to be 10 to the minus 100 because so if I'm doing string theory, I don't care. Essentially the sigma model doesn't care about the torus of the volume of the torus. The sigma model is a good description for any volume, if you want. So if you take it to be 10 to the minus 100. Then you can get the R stretched to be like.
It could be, although that wouldn't change. That in computing these quantum fluctuations, I didn't assume this. This was a statement to try and understand why quantum fluctuations should be large. It's true that if you're working in string theory and you somehow want to work in the wrong T-dual frame, you want to work in the frame where the compact manifold is much smaller than string scale. I don't know why first of all, it's this formula would change if you worked in string theory, because I would suspect that you would get string theory just doesn't see compact manifold smaller than string length, right? Because you try and make it smaller than string length, it grows big again. So it's it's not clear what this formula would be if you did at least I don't know what the formula would be in the string sigma model, but I suspect that what you might get here would be really the size of the compact manifold that the string theory sees, which is always larger than 1. You try and squeeze it smaller than 1, it always becomes larger than 1. Now the second statement is about whether classical solutions are valid at all. So classical solutions, so there are clearly some solutions which are good solutions. What I'm talking about here is a typical solution. So most of the entropy is coming from solutions which are Planck size. There are of course some solutions for which quantum fluctuations are small. This is not a statement about all solutions being bad. All solutions are not bad.
The solution, the only way to throw it away is to find some distinct. So okay, if the curvature of the solution is large, then okay, I'm very happy.
No, but if quantum fluctuations about the solution are large as classical expectation values, then those solutions are bad solutions. So the statement here is that most of the entropy that Ritschkoff counted is coming from solutions that are unreliable. That is not the statement that all solutions are unreliable.
But this was normal Unimadas and Amaus. This was not because if you look at the typical state in the D1 system, the curvature of the typical states of the typical, and this was described by Polchinski and Pullman and people.
Yes.
So this has been known for a long time.
Okay.
Solutions, you know.
So most of the entropy is coming from unreliable solutions.
Yes, for the two-chart system, this is like, you know, ancient knowledge.
Okay, fine. So if you agree on that, that's good. Yes. Yes.
So you know.
This is not a curvature reason. This is.
No, but the question is there any geometry in the two charts?
Yes.
The curvature is small.
Of course, there are geometries where you just take the profile to be very big.
And your quantum fluctuations are large.
Yes, I think are large or small.
Large. So quantum fluctuations large, but curvature small.
I don't know. Maybe not. It could be.
Since you have everything, you know, can you just? You know,
we could check. I don't know the answer immediately. I can't tell you the answer immediately. You'll have to compute quantum fluctuations. You could take different profiles and you could compute these quantities there. I would suspect that if you take big profile functions, those are solutions for which curvature is small, and those are also solutions for which quantum fluctuations are small.
no, but those are atypical.
Those are atypical. That's right.
No, but if you take a solution for which quantum fluctuations are large, I think in the two-chart system, this automatically puts in the regime where curvature is large.
Okay, but these are the typical solutions. So what is the two-charge entropy counting then telling us if it's all coming from unreliable solutions?
So I think this was known for a long time ago.
But what is it telling us? And we still use the two-charge.
Theory when you can't rely on physics in one regime, especially when you have a lot of supersymmetry, like here you have 8 supercharges, there are other descriptions in other regimes which give exactly the same physics. There are non-normalization theorems, for example. So, for example, if you compute the phase space of these solutions, you know, this entropy which Raju computed, for example, was computed by Marov and Palmer long time before that using supertubes. So if you look at the supertube Born-Infeld action, you can quantize supertubes in the Born-Infeld action, you find exactly the same results as Raju.
But you know, counting the entropy is something which often works. You know, you can also count the entropy at the orbifold point because these half PPA states are just protected. But that doesn't mean that the orbifold point is giving you an accurate description of the physics near r equal to 0. The question I'm asking right now is, are you getting an accurate description of the physics near r equal to 0?
If I describe a supertube using a Born-Infeld action of a brane which is composing it, then I have an accurate.
But quantum fluctuations need to be small because you're still finding the supertube by solving, you know, classical equations of motion.
No, that's the whole point. So supertubes have 3 descriptions. One of them is as classical solutions.
Okay.
The other one is as Born-Infeld action solutions.
Okay.
The other one is as matrix model solutions.
Okay, so
they are different in 3 different regimes of parameters.
Okay, so
now,
yes.
You are telling me that one regime of parameter doesn't work anymore, and when you compute the black hole entropy and so on and so forth, the typical states are not described by physics in that regime of parameter. But again, as a example,
but there's no regime of. I don't understand what regime of parameters is going to describe the physics near r equal to 0. Maybe you can explain to me, and maybe you can explain to me. But I don't understand that there's any regime of parameters in this setting that's going to describe typical states near r equal to 0. It seems that there are clearly some solutions, some big profile solutions, including maybe profile solutions which are string scale, which can be well described by classical string theory. But the typical entropy is coming from profile functions which are Planck scale, and it doesn't seem to me that classical string theory can describe those profile functions. Now, if maybe there's some dual description we can switch to, but I don't know what that dual description is. It seems that this is, yeah.
So, in your second bullet point here, dilettante should not blow up. So
yes.
Q1 over Q5 has to be order 1.
Yes.
Where does that come from?
That comes just from the formula for the dilettante. It was this. So this is Q5 over Q1.
Yeah, but to me that's just a statement that you're working in the wrong duality frame to describe R near 0. So one of the things that makes things work better for us is that we're working in the NS frame, which is S dual to the frame you're working in.
So it's okay. I mean, first, so that's like this original double Kerr-Harvey solutions. Is that right?
No, this is the NS5 range.
Yeah, it's F1 NS5.
F1 NS. Oh, so they were working in F1P. F1P. Okay. Okay. So maybe we can talk more about this. Maybe there's some other frame you can go in which these quantum fluctuations are small, in which you can. But certainly in the D1 D5 brane, these solutions are not reliable. Maybe you can describe them in some S2L frame.
Well, so the way it's working is that in that frame,
yes.
It's reliable when the F1 charge is really large, and then the 5 branes are basically some. You should think of NS5 branes as like classical solitons.
Mm-hmm.
Of the sigma model, of string theory, and so as long as you're in some regime where those solitons don't have some non-abelian structure, you're sort of like well onto the Coulomb branch of multi-soliton dynamics, then everything's very reliable. and very classical, because
Okay.
it's basically soliton physics. It's stringy,
Okay.
but it's
It-
like soliton physics.
Okay, it could be. I mean, it maybe there's some other S2L description of this which gives you a good description. I mean, the question would be, what does that description tell you in the D1 D5 frame when about the physics near r equal to 0?
I think the way to say it is that
Yes.
every duality frame has its own regime of validity, and so you should be working in the one that gives the correct low energy physics.
Well, there's certainly some. I mean, yeah.
And so there was some analysis that I did with a student like 20 years ago about starting with actually the non-extremal two-charge geometries and asking what happens as you start cranking down the temperature. And you find that the physics at the horizon, as you start cranking down the temperature towards extremality, goes through a whole sequence of duality transformations as to what's sort of the correct low energy description near the horizon. And you always find out that the lowest temperature things are in the duality frame of F1P, which is why the F1P geometry counts the microstates of the two-charge system. But I think it's an indicator that if you want to say what's happening near r equals 0, then working from one duality frame and then concluding that it breaks down long before you get to r equals 0 is just a statement that describing that physics is better done in a different duality frame.
Okay, it could be. I mean,
again have descriptions in the duality frame.
Okay. It's possible that there's some other dual description, but let me just make the following limited point. The limited point is that and which I wanted to illustrate using this was there's a quantum corrected geometry which you can compute here. That quantum corrected geometry does differ at Planck scale from the conventional geometry, and at the point at which it starts differing, you can compute in this setup also quantum fluctuations, and the geometry becomes unreliable. Now, maybe in this case, and we can discuss more. Maybe in this case, you can switch to a dual description in that setup. But the claim is that this is in general what you expect to happen. If you try to quantize fuzzball states, that you would have you would find these microstates. These microstates would differ in the regime, which was Planck scale from they would start differing at some Planckian scale from the conventional geometry, and at that point they are unreliable. So this is my typical point, and maybe in some cases you can switch to some description where you can describe them well, and we can talk more about this. Okay.
But again, I think for the supertype, so there's a more subtle story which was worked out by Pochinski and Pochinski.
Yes.
If you look at the geometries and if you look at the fuzzballs, you have to actually change duality frame as you look at.
Indeed, you have to change duality frame. So you're right.
So there's one thing about
so we can change.
And I totally get that geometry breaks down.
The point I want to make actually. Yes, but the point I want to make is about the general idea of taking supergravity solutions and about quantizing the supergravity solutions. It might happen that in this particular setup where you're trying to describe Riemann states of the D1 D5 system, there's some other duality frame you can go to where you can with some effort find a description of physics near r equal to 0. But the point I want to make, which is what this calculation illustrates, is that in general, if you try and find supergravity solutions, the typical supergravity solutions will differ at Planckian scale, and at that point they'll become unreliable. And very often, So in this case, by the way, you expect. Let me just say one more thing. In this case, there's one more difference which from the standard setting, which is in this case you expect that there will be some exotic physics near r equal to 0. In the conventional black hole, in fact, at the horizon, quantum fluctuations are small. So you do have a reliable geometry which describes that physics. And I would suspect that in the conventional setting, just that geometry will continue to describe the physics. In this case, there is actually an interesting question about what happens near r equal to 0. In the case where you have a macroscopic black hole, there is already a candidate for what happens near the horizon, which is that physics continues to be described by the conventional black hole geometry. Okay, so you're right. In this case, there's an interesting question, and clearly, as I said at the beginning, the conventional geometry also does not give you an accurate description of physics near r equal to 0, which is clear from the get-go. And so this setting is slightly different in that setting, in that regard. But the moment you have a macroscopic horizon, the conventional geometry does not suffer from the problem that the quantum fluctuations are large at the horizon, whereas these geometries you suspect will. Okay. So anyway, this is this other probe W field that we computed. This has the property. It was interesting because the difference parameter is always 1 because this guy is always 0 in the conventional geometry, but this quantumness parameter is always large. Okay. So this value, which you might have thought always differs significantly from the black hole, is always unreliable. Okay, even when you're far away. Okay. Okay, so let me just say this is what I wanted to say, which I just said, that we can compute the average quantum corrected fuzzball geometry. This differs from the conventional geometry at the Planck scale, and at the point where it's interesting, it's unreliable. And as we discussed, maybe it's possible to switch to another description which is reliable, but these solutions have this problem. Okay. Now let me just say, there's a question about why the right entropy emerges from these unreliable solutions. Maybe the discussion we had right now clarifies this question. But this is the point we just discussed, which is the fact that most of the entropy comes from Planck-sized fuzzballs. Okay, so you can do that just by estimating the size of the profile function, and that size is given by some number which is proportional to tau. In fact, even fluctuations in this size are given by some number which is proportional to tau squared. That tells you that most of the entropy is coming from Planck-sized fuzzballs. And so you could ask, how did the right entropy emerge from unreliable solutions? Maybe one answer is that you can switch to some other frame where these solutions are reliable. But I think that another way you can understand this.
When you do switch to that frame,
yes.
It becomes the string scale.
So
the statement that the geometry, that
yes.
the entropy is matched by computing the entropy of F1p
yes.
is precisely the statement that you get the entropy from counting strings. So it's a statement that you're at the correspondence point in the right duality frame.
So something I want to understand is, so if most of the geometry is coming from Planckian solutions, that's not something that will change if you change duality frames. If you change duality frames, you can't change Planck scale away from Planck scale.
Yeah,
so now maybe you want to be in some different regime of parameters.
Before you went down to r equals 0, the curvature became string scale.
That's correct.
Okay.
And you have to dualize yourself out.
And you have to dualize yourself to someplace where it's not.
So maybe you and maybe you also do some U-duality transformations to change the value of Q1 and Q5.
Yep.
Okay, so because you also want to be in a regime where Q5 and Q1 are very different.
You don't have to do duality, you just have to dualize yourself.
So I think I thought you just explained that you want to be in a setup where Q5 is small and Q1 is very large, or N1 is very large.
For gravity Q1 is programmable.
Is what?
For gravity Q1 Q5 and there's a number Q1 Q5.
Depends on which
number Q1 Q5 are frozen.
So the description Emil was just telling me, I thought it requires you to do U-duality to go, you can keep N1 and N5 constant and do U-duality to change N1 and N5.
So in the comments there were two papers that I was referring to. One was a paper from a year ago with Stefano, one was another paper from 15 years ago with somebody else. So the 15 years ago calculation was this sequence of duality frame chasing that Polchinski and Poom used more recently. And so in that story, it's the case that the reason that the entropy comes out to be the F1p entropy is that in the appropriate duality frame, what you're counting is string entropy. And more or less the statement of the Horowitz-Polchinski correspondence principle is that the correspondence point is where the black hole entropy matches the string entropy. And in this particular case, it's when you start doing the duality chasing, you find that the geometrical description in the appropriate duality frame reaches a point where the curvature at the horizon becomes string scale.
Okay.
Not that the curvature at the horizon becomes Planck scale. If it became Planck scale, I think you wouldn't. You would have no reason to expect that.
You're out of the. You move out of the duality frame well before. Fine.
To expect that the two-charge entropy is accounted for by quantizing.
Actually, I would think that there was yes. I would think that there's just
lundi, mardi, mercredi, jeudi, vendredi, samedi,
Yes, it's still long. Thank you.
That's the same, right? But in fact, I would think that there's another reason, and I think this may be one reason why I would suspect the program of counting entropy using fuzzballs might be more successful in the program of describing physics in the interior, which is the fact that there are clearly some regions of phase space in which you can count solutions reliably. Now, it may happen that for supersymmetric solutions, you can just extrapolate your answer from the regions of phase space where you can count reliably to regions of phase space you can't. Okay. Now, these duality transformations are not something so the fact that once again you can do these duality transformations and go to some physics which is reliable happens, I suspect, in this two-charge setup, and is not something you expect will happen in some macroscopic black hole setup, because there's just a candidate geometry which is already reliable. Okay, but I think that this is one reason why counting entropy is maybe a more fruitful thing than trying to understand physics in the interior. Okay, good. So this is what I had to say about two-charge solutions. Let me say a little bit about these multi-charge solutions, which were found by Benna and others. As we discussed, Lunin-Mathur geometries are slightly special because they correspond to solutions that do not have any horizon classically. But now, of course, we found many solutions with the same charges as a macroscopic black hole. So a very recent large class was found here over the last 2 years. So we're going to look at these solutions. So these are the solutions. This is the metric, which you've probably heard many talks on. These solutions are asymptotically ADS. That's nice because we can use ADS CFT. They're labeled by many integers. They're labeled by some integers n, m, and k, and some 3 numbers a, b, and ry. We'll actually consider only some subset of these solutions, which are the solutions which have k equal to 1, m equal to 0, and arbitrary n. The reason we look at this is because these were the solutions for which the metric was given explicitly in the first paper. Yusuf was very kind to send us a description of the metric for more general values, but that involved solving some complicated differential equation to get the metric. So I think we'll restrict ourselves to this set of parameter space. But I think the results I'll describe will very easily generalize to more general charges, to more general values of these parameters. Okay, so here's a description of the charges. So these guys have some angular momentum on the S3, so they are asymptotically ADS3 cross S3. They have m is equal to py, so they are BPS, and they have some angular momentum. Now there are some parameters here which are b and a. I'm going to define the ratio of these 2 parameters to be kappa. Okay, this is one parameter I'd like you to keep in mind. The asymptotic ADS radius is given by this, and the way I tend to think about these solutions is that I tend to think of b as being roughly the asymptotic ADS radius. So in some units where the ADS radius is 1, b is order 1, and then this parameter a will control the size of the fuzzball for me. Okay, so I hope we're happy with that. Okay, good.
Sorry, what was lambda?
Lambda is the asymptotic ADS radius. It's lambda to the 4. Lambda is the asymptotic ADS radius.
So this is in Q1, Q5.
Square root Q1, Q5, yeah. Is it good?
Yeah, I don't think I'm super happy about that, but go ahead.
About this statement?
Yeah, I think b is a free parameter which you can make.
B is indeed if. Yes.
I tend to think of b as it's the radius at which you cross over from asymptotically ADS3 to something that's ADS2 cross S, an S1 fibred over ADS2.
Very good. So if you think of
So
if you think
that can happen at any radius.
Indeed, it can happen at any radius, but so it's true that b is a free parameter.
B is a scale that's set by the momentum charge.
B is indeed a scale that's set by m. I agree with
so a
that.
statement that the momentum charge is always of order the ADS radius squared is definitely not correct.
Okay. Anyway, there's some precise formulas here, and the main thing I want, the main point of this bullet point is that I want to think of this ratio b by a and thinking of a being small as a small fuzzball. But you don't have to take this. All of you know these solutions well, and so let's just think of these formulas. Okay. So okay, good. So now here's what I'm going to compute. What I'm going to compute is a 2-point function of some marginal scalar operator. Okay, so I'm going to take some marginal scalar operator on the boundary, which corresponds to a massless scalar propagating in ADS. I'm going to compute the 2-point function and compute the Fourier transform of the 2-point function. This is a Whiteman function, so I won't compute a time-ordered product. I'm going to compute really the product of the operators, compute the Fourier transform, which we can do using standard ADS CFT techniques. What are the quantities of interest? So here are 2 quantities of interest. First, you can prove that if you look at the thermal Whiteman function,
Who is gamma, sorry?
gamma is the momentum along the y direction. Yeah? Okay, so this has frequency omega and momentum gamma along the y direction. Now you can prove that if you look at the thermal Whiteman function and you look at the limit of large gamma, where the momentum becomes much larger than the frequency, so it becomes very space-like, then you can prove that this Whiteman function has to die off at least as fast as e to the minus beta by 2 into gamma, where beta is the minimum of the left and the right temperatures. In this case, one of these guys is infinity because they're BPS, so it's only the other guy that enters. It's only beta r that enters. Okay. Second, you can prove, so this is a bound you can prove using, which is true in any relativistic quantum field theory, that the thermal Whiteman function has to obey this bound at large gamma. Second, it's known that black holes saturate this bound. Okay. So black holes are the case where if you take this limit of this Whiteman function, it becomes beta over 2. Okay. And the reason black holes saturate this bound is because physically the near horizon region allows arbitrarily space-like modes to propagate. You say you might have thought that these modes with gamma larger than omega shouldn't even exist, and indeed they don't exist in flat space. You can't have modes which have momentum larger than frequency. But you can have such modes about the black hole because the near horizon region allows modes which are very space-like to propagate. So you can have arbitrarily low energies given arbitrarily large momentum, and these guys can propagate in the near horizon region of the black hole. And the black hole does as efficient a job as possible in allowing these modes to propagate, and therefore black hole geometries saturate this bound. Okay. So the question is, do the fuzzball solutions, do they saturate this bound? Okay, that's a natural question you can ask. So this is it's a sign, it's a speciality of black holes. It's like the chaos bound, if you like. It's simpler to calculate, and the question is whether fuzzball solutions saturate this bound. The second thing I want to compute is this gap between excitations. It's the fact that the gap between successive excitations is, if it is order e to the minus s, as we discussed, then the thermal Whiteman function should have an effectively continuous spectrum. More precisely, if you take this Whiteman function and you smear it slightly with any smearing function with a gap larger than e to the minus s, then this smeared function has support for continuous ranges of omega naught, okay, for continuous ranges of frequency. Okay, so the question you can ask is whether the Whiteman function has support for a continuous spectrum of frequencies or not. Okay, so these are the two physical quantities of interest. Okay, so here's how. So now the technical part is simple. We just because we are looking at a marginal operator, we look at a massless at a minimally coupled scalar. In the bulk, this wave equation is separable, which is already noted by a couple of groups. Of course, we consider propagation with no angular momentum. This is again the statement, it's some marginal operator, doesn't have any mass on ADS3. And then this wave equation is separable, and so you can separate phi into some radial component psi, and this frequency and angular momentum, omega and gamma, as we want. Okay? So doing the Fourier transform now becomes very simple. You just need to find this radial part. Okay. So in this radial part, you can convert this into some WKB form. So you can write the radial wave equation in some WKB form. It's convenient, as I said, to write B is A kappa. Kappa is this parameter B by A, and convenient to change variables to this psi, which is R over A. So rescale all units in terms of A. You get some potential. Let me just plot the potential for you. So this is the graph of the potential versus the radial coordinate. So this is the graph for different values of n. Okay. Now let me point out that for the black hole, this potential would have dipped and it would have kept going down. Okay. So for the black hole, the potential would just have kept going down to minus infinity. For the fuzzballs, it turns around and it goes up again. Okay. So that's the difference between the potential for wave propagation in the black hole background and the fuzzball background. It's a question of whether it drops or goes up. So this is for various values of n, as I said, for omega equal to 0, gamma equal to some number, and kappa. Okay. Is everyone with me here? Okay. So now we can solve this. Of course, if you're at large gamma, you can check that in fact you can use the WKB approximation, and you get some quantization condition, okay, for the allowed frequencies. The quantization condition is just that between the two turning points of the potential, which are psi 1 and psi 2, the integral of the square root of the potential has to be quantized. Okay. This gives you a quantization condition on the frequencies. It tells you that the frequencies are quantized in that the gap between neighboring excitations is proportional to 1 over kappa squared. Remember, this was a ratio of B by A times some order 1 number Gn, where Gn depends on this n, which was a function of geometry, and here's Gn for the first 5 values of n, for n equal to 1, 2, 3, 4, and 5. Okay, and you can keep computing on Gn.
So kappa is A over B or B over A?
Kappa is B over A.
B over A. So there's going to be A over B. There's going to be 1 over n on it. So if I look at the biggest, so if I look at the state which has the longest throat.
That's right. It's 1 over n 1 and 5. So that's still.
It's actually 1 over n over 5 squared. Kappa squared.
It's
kappa
1
is 1 over n over 5.
1 over n 1 and 5 squared. Yes.
Yeah, that's quite weird because we are also solving the wave equation in some backgrounds. If you just look at the mass.
Sorry, I think that a squared is 1 over n 1 and 5. If I get this right, if I understand correctly, I thought you wanted a squared to be 1 over n 1 and 5 because you wanted JR to be 1. So a squared is 1 over n 1. So kappa squared is 1 over n 1 and 5. So you will get 1 over n 1 and 5. It's the same. I think it's the same result. But that's an atypical. I mean that's not the set of most general charges. And as we discussed, that's still too large. Now in that setup, I don't think the classical solution is reliable.
Where's the momentum in this game?
The momentum is. This is in the WKB thing. I'll give you an exact answer for a second. For now, this doesn't depend on momentum at all. It is just the frequency. This is true for large gamma. Okay. You can ask what happens, so you can check, if you want to do it for general gamma, you have to solve the equation numerically. So you can check, this is a function of delta omega versus kappa for gamma equal to 100. You could do it for different values of gamma numerically. I don't have that plot. But you can see that for large values of kappa, the WKB approximation is excellent. Of course, you could go to some general regime where both gamma and kappa were small, but you know, it's fine to look at the regime which has large gamma. Okay? And you see that the gap between frequencies is too large. It's far too large to represent you know, anything like the typical microstates.
Why? Okay, so sorry, the gap between frequencies is exactly 1 over 905.
Well, first of all, that's too large. But first,
the gap from the ground
yes.
state to the
Let me
first
say.
state.
Let me.
So all the arguments.
No. Sorry. This is a gap between successive excitations. Sorry, this gap I had here was gap between successive excitations.
Yeah, the earlier part of the talk argued that needed
Yeah.
to be e to the minus n1 and 5.
So this is
That's
that's
the gap on top of the first.
no. This is not the gap on the first. This is the gap between any two successive excitations.
Yeah, but also
In fact, this is
on the
not
first.
no. In particular, in fact, it doesn't give you an accurate description for the first, because this is really a gap between two successive excitations. You see, the first could be here, and then delta omega could be both positive and negative. So this is all really giving you the gap between successive excitations.
But
And
you
the gap
can
between
also compute
success.
You can also compute the gap between the first and the.
That's actually a harder calculation. It's not so easy to read that off from this quantization condition, because you see 0 could be anywhere. Yeah.
No, 0 is supersymmetric.
Well, in this frequency, you know, this is a question of an excitation
Yeah, but
of omega.
The momentum is supersymmetric. So the excitation you are putting has some momentum.
Has some frequency.
Sorry.
Has some frequency.
And some momentum.
And some momentum.
Large gamma.
And
So
some momentum.
if
That's
you
right.
put the momentum to be right moving, then you know then you are supersymmetric. So you can put the momentum so that you know this is going to be a supersymmetric.
But then that would be omega equal to gamma you're talking about.
Yeah.
But the omega equal to gamma as well. So this is not near omega equal to 0. The gap from the 0 thing is what you're talking about is the gap between omega equal to 0. Here I'm talking about the gap between successive excitations. And that gap between successive excitations is too large. But let me just say something.
Single solution. So on top of a single solution.
Yes, but
this is perfect.
no, that we discussed extensively before about whether on top of a single solution, I think the gap should still be e to the minus s. Let me just say one thing.
Okay.
Let me just say one thing. For the solutions that you have, the typical solution, you know, the solutions with a square equal to 1 over are some small subset of the solutions. The general solution you have as a being order 1. That's the setup. That's the general solution that you find has a and b both being some order 1 parameters, right? Because you want JL and JR to have some values.
From the CFT perspective, you know that the best.
No, but let's look at a solution which has a equal to order 1, which has some given value of JL and JR, and then the gap is way too large. It's just
those are typical.
well. So now we can look at the special solutions which have, you know, which correspond to the non-rotating D1 D5 solutions. First of all, I think if you set a equal to 1 over a square equal to 1 by n1 and 5, that solution becomes unreliable for the argument I presented previously. You know, you look at.
I don't understand because the curvature is small in that solution.
Well, yes. Let me come to that solution at the end. But let me just first point out that for when the moment you take a being order 1, these solutions are way too large. Second, even if you take a square to be 1 over n1 and 5, this gap is still too large. Okay, this gap is still too large because of the discussion we had here. You know, the gap should be e to the s on.
These 2-point function is taking one geometry and is looking at extension.
Exactly, and we argued that this wasn't a good thing to do, right?
You're just jumping from the ground state of one geometry to something of the same.
No. I could look at successive, but so this doesn't, in typical statistical systems you do jump to the side.
You're a zero energy, so let's stick to zero temperature.
Let's look at successive excitations.
No, I don't want successive. I'm at zero temperature.
Why don't we look at
temperature? This is a zero temperature solution.
Yes, but we can still look at two different excitations. We could look at one excitation to here and another excitation. So I'm looking at delta omega, which is omega 1 minus omega 2, where both omega 1 and omega 2 are allowed frequencies.
On top of which?
On top of the solution that you have.
So if you look on top of one particular solution.
One particular solution.
Zero temperature.
Yes.
And you look at 2 layers.
Yes.
That should be of order 1.
No, it should not be. It should be of order e to the minus s. You know, you may say that the lowest state, and this does happen, for example, in the Stanford Witten calculation, sometimes the lowest excited state is indeed 1 over n1 n5 above this, but every state after that, always there's a continuum. You always get a continuum, which is e to the minus s.
But that's, again, you're getting
that's something you see in. No, not because of other states. The continuum of excitations. No. The tower on top of it, as we discussed extensively, about a single state does not have this property. You know, the tower on top of a single state might have a gap from the ground state, but then has a continuum at e to the minus s.
No, I don't think that's.
But this is just true in most statistical systems. You can compute it.
No, if you look at the zero temperature state.
We can look at this Witten Stanford calculation.
So
you
do
can.
you agree that the first state is 1 over n5?
Is what?
Do you agree that the first state?
The first state I don't know, but it could be n1 1 by n1 n5. The first state, first of all, I don't know the answer to that. But
Okay,
even if the first state has a band gap, the successive states do not have any such band gap. That would be an extraordinarily atypical statistical system. You know, it would be the statement that the CFT, which is dual to ADS3 process.
What you are computing, you are basically taking one geometry configuration and you're basically exciting it, and when you excite the geometry, you're getting 1 over n5,
But where,
2 over
but that's,
n5, you're getting the whole
but I think
thing.
that's telling you the geometry is giving you the wrong answer.
No, the calculation you're doing, you're exciting the geometry.
Yes,
with the wrong
and you don't,
data.
and you shouldn't get
You're
1
not
by n1 and
exciting
5.
to the guys which are transfers.
But I'm just exciting the geometry. You give me a geometry, so I'm computing this 2-point function, right? I'm just computing this 2-point function. This 2-point function should have a continuous spectrum when Fourier transform. In the CFT, I claim that this 2-point function will have a continuous spectrum. I'm just, I mean, there's no sideways and forward. The question is just about a single eigenstate. I compute this 2-point function. Should it have a continuous spectrum or not? It should have a continuous spectrum. It doesn't have these gaps. It doesn't have these big gaps in frequency. That happens about the orbifold point, and that's the wrong answer the moment you turn on moduli.
Yeah. The thing which is weird, again, it happens in the bulk and at exactly the same values as orbifold points.
But
there's an infinite number of
no, but then one should be skeptical of things which shouldn't match.
No, but that's
because the bulk calculation.
If numbers match, then there's a question. As a physicist, coincidences don't happen. So if you tell me that these numbers are completely scrambled, and I find an infinite tower or 2 infinite towers of numbers which match,
I think that's because you look.
As a physicist, you have to wonder why.
Well, I think that's.
There's a calculation. Indeed, it doesn't have the right to match, and there are generic arguments. But the moment you find no calculation, and then the towers match, and you have an infinite number of numbers which matches. Then you have found
well, the infinite numbers are just that the gap is matching. First of all, I think that these solutions where you take a square being 1 over n1 n5 are solutions which have a problem. Well, let me just say it.
I don't think he's disagreeing with your calculation, Yosef. I think he's saying that if you go calculate thermal things in the black hole, geometry, you get an answer. The answer is.
But the black hole doesn't have the first gap, for example. In the black hole, you can never get the 1 over n5 the first gap.
Yeah, so I think, therefore, I think one would say that your state is far from being a black hole or having anything to do with the physics that's coming out of the thermodynamics of black holes.
No, for the black hole, the only argument he has is about the states which are above. So he's computing energy between state numbers 5 and 6. Okay, those could be to the minus s. I have no problem.
But that
the energy between
if
the
the black hole
state and the first state.
Well, first of all, let's not. First of all, the answer is really between energy 5 and energy 6, and let me just say that the black hole gives you an answer which is continuous, and the CFT also suggests an answer which is continuous. The general statistical systems have an answer for this kind of spectrum which is continuous. Yeah, e to the minus s, but much larger than 1 over s.
But the first gap, the one above the ground.
But why are we? But this is not an answer for the first gap. This is not an answer for the first gap. This is an answer for successive excitation.
The black hole solution doesn't give you the right answer for the first gap, and the first gap is captured by those guys perfectly. So.
Well, I don't. Well.
So the first gap is 1 over n5, and the black hole doesn't capture that. Those guys capture that. So the conclusion is, and it matches the CFT first gap. So then if I have something which in the bulk matches the CFT, and I have a matching, and the black hole doesn't match, then okay.
Well, I think
maybe you are saying that the extremal black hole is a bad approximation, or one should throw it away. Well, the moment you go above extremality by something, one should look at black holes. Then
Can I say? But there's a statement you have maybe what you want to claim is that if someday, well, actually these are calculations for 2-dimensional CFTs we can probably already do. But you're saying that these energy eigenstates in 2-dimensional CFTs have the property that when you hit them with a marginal scalar operator, you tend to go up in towers like this. You don't go sideways. That's a statement that these are very, very special statistical systems.
No,
it's a very strong claim.
Your operators are very special.
My operator is a general marginal scalar operator. I could use a stress tensor.
That's a torus mode, which is not part of the consistent truncation.
Is what
That's a torus mode. So the ones which we solved, these modes which we solved, which are linear, they are the modes which are basically
they're not
geometric fields on the torus. So those
why are they looking at?
Sorry.
Okay.
The modes you are calculating.
But this is a very generic answer. You could do this for some any scale. You could do. It doesn't even have to be a scalar. The moment you quantize, the fact that this gap is proportional to 1 over kappa square is just a statement that this throat caps off at 1 over kappa square. You compute any operator in the bulk, and you will get these numbers will change, but you will get something which will go like 1 over kappa squared. That this doesn't have to do with this special mode. It's just something which is very generic.
It's just a statement that the gap is governed by the redshift to the.
That's right. That's right, and that redshift is too large in the Fuzzball solution.
That the cap being finite is very different. From being in finite redshift is very different from the cap being in infinite redshift.
Yeah, I agree. Yeah.
But I think computing the tower on top of the same gap is not actually what you're meaning. So if you take the same state.
Yes, and I just compute this. This is the tower in the same state. This is 2-point function. That's what ADS-CFT tells you to do, right? Tells you to compute expectation values in one state. 2-point function in a single state. So this is 2-point function in a single state. You know, you're right. We don't have a proof, but you maybe, you know, this is a sharp claim if you're saying it's coming out of the solutions, which is that this 2-point function in CFTs with a holographic dual, in particular in the D1, D5 CFT at the supergravity point, has, you know, does not have a continuous spectrum but has a gap spectrum. That could be a statement you're making, but I should say that's a very strong statement.
That's what the calculation says.
Well, that's not what the black hole calculation says. Do you see, the calculation could also be interpreted. It could also be interpreted to say that these states you're finding are very atypical states.
Sorry?
It could also be that the states you're finding are very atypical states.
So the black hole can never give me the ground state. The ground state is the first state, which is 1 over n, which again, I can get it both from the CFT and I can get it from both from the microstates. And the black hole
Actually,
can never give it
sorry, how do you compute this energy gap in the CFT at the supergravity point in moduli space?
You don't compute it in CFT, but I think it's.
How do you know that that's the right answer? Even, I mean, in some cases like the SYK model, you can compute it. But sorry, but you said that but the first excited state, I don't know how you compute that in the CFT once you've turned on the modular. You computed the orbifold point, which is just totally wrong. I mean, that's not the right answer for the supergravity point.
But then again, I get an infinite tower at the orbifold point, and I get an infinite tower supergravity, and there's a perfect match.
But that's because you're finding the supergravities.
So you claim that from
at the orbifold point, if I have the first gap.
No, but the orbifold point is a singular point in modular space, which is already far away.
Indeed,
from
and then I compute there, and I get an infinite tower.
So I guess
and then I compute in the bulk, and I get an infinite tower, and the infinite towers match. Perfect.
That's I think a statement that the solutions you're finding are inspired by the orbifold point, and so you're finding solutions which somehow have similar properties to some solutions in the orbifold point. But you know, it's a statement that the solutions are not typical solutions. It's, you know, that's a statement that's a statement of the solutions. Say, you know, the fact that the solutions are inspired by some profile.
So for example, if you look at the orbifold point, the typical the states which have this gap have the longest possible strings, which are the ones where I build the Strominger buffer entropy. So
yeah, but these longest possible strings. Yeah, but the moment you turn on interactions, this 1 over n1 n5 will just go away. You're right. This 1 over n1 n5 comes from these long strings, and that's because the orbifold theory is effectively free. The moment you turn on interactions, this will just totally vanish.
But I think the gap
everything will spread.
I think the gap from the ground state to the first excited state.
It could be. Can I say, actually there is an example in which you can calculate this. It's this SYK model. So, you know, in the SYK model, it is indeed true that the gap from the ground state to the first excited state is indeed, you know, finite. Now, we don't know, I don't know how to do that calculation in the D1, D5 CFT, but that's a possibility which I'm willing, which could be true. But, you know, the fact that the gap after that is finite, it just seems very weird. It could be that the gap, you know, they're short representations, and for some reason there's some forbidden band gap of energies. That could be, we know some examples. Although I don't know how to compute that in the D1, D5 CFT. I don't think that calculation has been done. And in the SYK model, we don't have a black hole dual to compare it with. In fact, it may well be that there's a continuum right above short representations. That's the most generic setup, right? That you just have short representations, and there's just a continuum of long representations all above it. You know, and that's indeed what the black hole suggests. So it's not clear the black hole is giving you the wrong answer ever, but the fuzzballs are giving you some answer which is very, very strange, right? Okay, let me just go on to. I'm coming to an end, but this is the statement which we just discussed. Let me just say that the gap between excitations is order 1, at least for the cases where kappa is order 1, which is indeed the cases where you have JL and JR. That's actually suggestive, I think, of a phase of zero entropy. You know, if you computed a gas of graviton, so if you looked at thermal ADS and you computed the energy gap between successive excitations, that gap would also be order 1. That's because thermal ADS has zero entropy. So, you know, it is indeed true that you could have some subsector of the Hilbert space which is living in some faraway disconnected place, and that subsector of the Hilbert space has gaps which are order 1.
But so those excitations are above the ADS threshold. So you have an ADS threshold, you have a cap at the bottom.
Yes.
The physics of the black hole physics is expected to be at the bottom.
Yes.
Those guys which are computing on A and B are equal. Those guys don't even get into
A and B are not equal. These are setups where,
same order. So
by just order 1, I'm just separating order 1 from order n1 n5. You see, I don't want to put in, I don't like to put in factors of n in classical solutions, because I think if you do that, then quantum fluctuations become large.
But okay, that's what I have to understand, because I have a smooth solution, and again, when A is equal to 1 over.
Roughly, the reason is as follows. Let me just say what I think the reason is.
So this order 1 stuff is purely because you're considering ADS3. So there's an ADS3 infinity, so if you have fluctuations there, of course you have a gap of gravity and so on. But this order 1 stuff doesn't even explore the throat of the black hole.
So those
are not at all typical fuzzballs.
Okay, so these yes, but I just want to say things which have larger gap, including a gap being order 1 by S, are solutions which, you know, are suggestive of phases of which have very subleading entropy. They're very atypical.
Between 1 and 1 by S, then I mean, you know, there should be some difference on the CFT side.
Well, they're still suppressed, you know, compared to the entropy. In one case, the entropy is log S, in the other case, the entropy is 0. But they're still exponentially suppressed compared to typical states. Let me say something about long throats since we're having so much discussion about that. Okay, so this is the setup where you take A equal to L Planck. Okay, so the first statement is that a kappa goes to infinity and this large, well, I'm jumping ahead of myself a little bit, but let me just say something about the energy gap. So the energy gap is still too large because it's still 1 over s, okay, which is too large. Second, the A equal to 0 solutions represent only a small class of microstates of the ones you found, because JR is proportional to A square. So if you take A to 0, you also set JR to 0. Okay, but the question is, could these solutions be microstates of the non-rotating D1 D5 system? I want to point out that if you take A equal to L Planck, which is what you have to do to get your long throats, I think that these solutions are unreliable for the general arguments I mentioned previously. I would expect quantum fluctuations to be large in these solutions in the following sense. So let me just say a little bit about the A equal to 0 solutions. So this is what the metric looks like if you take A goes to 0 to take these very long throats. Is what if yes, it becomes BTZ. The limit is BTZ. Yes, but let me. I know you compute this metric. I'm just saying it for those who may not have looked at it. It's true when you take A equal to 0. This the metric, if you make a change of variables, becomes a metric of an extremal BTZ black hole. But in fact, if you take if you take the limit slightly differently, if you first take the limit r equal to 0 and then take the limit a equal to 0, you get a different geometry. Okay, so this is the limit when you take r equal to a psi and then you expand around psi equal to 0 and you keep a small. Okay, now you find the following. Let's say A is order L Planck. Okay?
Does this correspond to going to near inside the throat?
That's right. You go inside the throat and then you blow things up. So now you're sitting near the bottom of the throat and you're scaling that distance as you take A to 0. So you're exploring the bottom of the throat.
Then you get an ADS2 solution of the cap.
Yes. But let me say something about the ADS2 solution. You see, if A is L Planck, then I would suspect that fluctuations in A would also be of the order of A. Okay, this is just the fact that if you
Planck in some original units which now have nothing to do with physics.
Well, it's a question of So
you have an ADS2
yes.
solution, you have an ADS2
But the problem is when you have long ADS2 throats, the lengths of these ADS2 throats are subject to quantum fluctuations.
Why?
Well, it's a fact that if you have, so this is some parameter in the CFT, and I can't compute for you what delta A is because you haven't told me how to quantize the solutions. But if you gave me a coherent state that corresponded to these solutions, the question is what would be the spread of A in that coherent state? I suspect, by the way, if A is order L Planck and A is a good measurable quantity in the CFT, then I would suspect the delta A would be the same order as A, because just because of the uncertainty principle. Because if you try to pin down the value of A, you would have to construct some coherent state in the quantum theory. In that coherent state, there would be some uncertainties in the value of A, and if you took A to be so small, I would suspect delta would be.
JR, the minimum value of JR is 1/2.
See, you can't say, but you can't say that A is. Sorry, you can't say.
If A is bigger than by 10%,
Yes.
JR is 1.7.
But you can't say that A is quantized and also use A as a I thought you wanted.
No. So the point is, it depends on what perspective you have. If you
Yes.
look at an ADS3,
Yes.
from an ADS3 perspective, A is quantized. A is equal to JR, so JR can be 1/2, 1, 3/2, 2, and so on. So A is quantized, and if I choose A to be 1/2, for example, which is a value which is kosher, you cannot make it 0.7 because JR has to be equal to 1/2. So then it cannot fluctuate. It cannot. How can it fluctuate if JR has to be quantized?
Okay, good. So okay, good. So I was thinking, it's true that if you take A to be literally a charge, and A ceases to be a parameter in the set of solutions.
So A is. The point is JR depends.
Okay, so now you want to focus only on some solutions which are some subset of solutions. Okay, good.
I have JR equals 1/2.
Fine. Okay, good. So it's true that yes, it's true. A can't fluctuate, but you'll have to find some. Let me just say something about the argument, and then we can come to this. Okay, you're right that A itself literally may not fluctuate in the description you're giving me. In the description you're giving me, you have far from the right kind of entropy. But the point I want to make is the following. Let me just say is, when you have these throats which are very long, which are controlled by some parameter, the metric at the bottom of the throat depends to leading order on that parameter. I can't make this a precise calculation because you have to give me a quantization like there was in the two charge solutions. But you find that if you compute this quantumness parameter, then you in general expect that fluctuations of the metric are as large as classical values of the metric. And the reason for this is very simple. You see, the moment you put in explicit factors of n, or the central charge in the classical geometry, then you expect that there are fluctuations of the metric, and the length of the throat is a parameter you're going to put in explicitly in the classical geometry. Then you expect that fluctuations in the metric will be the same size as the metric. Because the moment you've put in n is a quantum parameter, you've put in a factor of h bar explicitly in a classical solution, and now you're looking.
Infinity, so
no, it's h bar. It's h bar. What do you mean h bar from infinity? It's a classical solution which has
the
a
classical solution has a throat which has some length.
yes, but that length has to become but the length of the throat scales with h bar.
Yes.
It's a now you can ask what is the fluctuations in the metric of that throat. Now you want to take the metric of that throat seriously, and I claim that since the length of the throat scales with h bar, I claim that delta g by g becomes order 1.
But my curvature is small and G string is small, so why
But curvature is not the only place where fluctuations come from. They come from the fact that in general you cannot pin down length scales, completely accurately in quantum gravity.
No,
In the two charts.
So here, for example, G right is 1/2. That's pinned down. I cannot.
Well, this is some very yes. But if you literally in this setup, take the setup that J right is 1/2, then you have one solution which is describing you've dropped some parameters totally. So now you have some very small subclass of solutions. I would suspect that when you find the full set of solutions that describe this non-rotating D1 D5P setup, there will be various parameters, and there will be one parameter which will be the length of the throat. In this case, I'm using A for a proxy of the length of the throat. In this subclass of solutions you found, the length of the throat is also correlated with JR. Surely you don't want that to be true of the general feature of solutions, right? The length of the throat is some independent parameter from JR. You want it to be an independent parameter.
Actually, it's unclear, but okay.
Well, I would suspect, well, you have to, this is a question you have to answer, but I would suspect that you don't want the length of the throat to be tied to JR. In principle, you would like solutions with large JR also to have long throats, right?
No.
Wouldn't you want them to have small redshifts? You want microstates of solutions states with large JR?
You can get a large GR and a long throat.
Well, there are black holes which have large JR.
No, because the black hole is supersymmetric, so.
The black hole can have large JR. What stops black hole? It's a Swettich-Larsen black hole, right?
No, but the black hole doesn't have a long throat. The moment you put a GR.
But a Swettich-Larsen black hole. This is a Swettich-Larsen. These.
GR is not supersymmetric. So the moment you say if your GR is large, you cannot get a supersymmetric black hole to resemble. So you don't get a long throat.
I don't understand.
Not all black holes are supersymmetric.
Sorry.
Not all black holes are supersymmetric.
Indeed, but then if you want to go, so in order to get GR,
So it's a question of what
non-extremal.
So right. So
then if you have to be non-extremal, so then your throat cannot be so long. Essentially your horizon comes up and basically
you
goes
can
up.
have extreme and non-supersymmetric.
No. So we look at GR equals to 0, and then you will look at GR above GR equals to 0. So when you have GR equals to 0 or to 1/2, then you have the black hole, and you have these microstates. The moment you make GR bigger than 0, you make it to be some fraction. There's no more supersymmetric black hole.
But
And
there
the
is
non-supersymmetric
extremal
black
black
hole.
hole,
Sorry?
but there are extremal black holes with both G left and G right non-zero, which can have very long throats.
But they're not going to be as long as those.
Sorry, but how are you going to get the infinite redshift now? Where is it? The energy gap of excitations about these solutions still should be e to the minus s, and how are your microstate geometries going to give you that energy gap, which is very small now?
No, again, if the microstate is supersymmetric, so the only thing which I can make is supersymmetric solutions for now.
Yes, but if you take
for
JR,
a supersymmetric solution, and I can compute.
I think setting A to be JR is a bit of a. Can I say let's take some parameter which is the length of the throat, which some I'm just using A for the proxy for the metric at the bottom of the throat. I presume when you find the full set of solutions, there's going to be some profile function or something which is going to specify the metric at the bottom of the throat.
And, sorry, my solution have low curvature.
That's a straitjacket.
No, but why should they? No. But I have a question about this fluctuation. So these fluctuations are supposed to, these quantum fluctuations are supposed to destroy the geometries. Now the geometries again have a large curvature. They have a small G string. So.
But
so you could say, let me restrict myself to the set of geometries which are BPS, and let's ignore quantization. Okay, so there's some very special class of solutions to of the field equations which are supersymmetric. In those solutions, the parameter A is tied to the parameter J right because you restricted yourself to that class of solutions. Okay? But if we're looking at the set of solutions of the full Einstein equations, I completely agree. There's some parameter which is how long the throat is. There's some other parameter J right. They're completely uncorrelated with one another, and the generic way you would expect black holes to form starting from some supersymmetric fuzzball is you tickle it a little bit, you made the thing non-extremal, and the energy and density that you want you just put in wants to collapse to make a black hole. So until you go away from classical GR, which has focusing theorems and energy bounds and all sorts of things which cause apparent horizons to form, you're going to be in this situation where you can fix J right and you add a little energy, and it makes the throat longer because the more energy you put in, the more things want to collapse into the black hole.
No, but the near extreme black hole, on the
Okay.
other hand, it actually has a horizon, the throat which is not large. So the moment you go away from extremality by turning on this J right, then actually the throat becomes, starts going up. You don't have this infinite throat where the
No, I would say fix J right, and now add some energy. Does the cap redshift? I think so. Because in classical GR, when you make the thing non-extremal, the focusing theorems tell you that the thing wants to get more redshifted. The horizon becomes closer to the stuff until at some point in classical GR, an apparent horizon forms, and the whole thing collapses into a generic black hole solution. That has to happen for sufficient non-extremality in classical GR.
Yeah, but that's not what we're talking here. Here we're talking about zero temperature.
Well, so I'm just trying to estimate. You see, in the two chart setups, I had a quantization, so I was able to give you some accurate estimation of what the quantumness parameter was.
But that
here
was
I don't have
that was because you had some U-duality argument that Lunan and Latour gave you that said within this infinite dimensional phase space of general relativity, there's some very tiny restricted phase space, which is the phase space of two-charge BTS solutions.
Yes.
And the Richkov analysis is quantizing that very
That's
restricted phase space where you're never leaving the supersymmetric locus.
That's right.
Okay. And so I think Joseph was trying to invent some three-charge version of that.
Yes.
Where you stay within the space
yes.
of three-charge solutions,
but there's no duality framework.
Can I say that the phase space that you find will presumably have some continuous function worth of degrees of freedom. It should have. It should not just be before quantization. Some continuous function worth of degrees of freedom, and one of those parameters presumably will control the shape of the bottom of the throat. There's some shape at the bottom of the throat. And what I'm trying to understand, and what I'm saying is that when you take this limit where you explore the bottom of the throat, I suspect I can't do the calculation because I don't have the quantization. I'll also complete very soon. The metric at the bottom of the throat will depend to leading order on this Planck scale parameter that you put in, and I suspect that will lead to fluctuations which are order 1, which are as large as this is a statement that it's a following simple statement. You shouldn't, it's a bad idea to put in factors of n explicitly into classical solutions. If you try and make throats which have a scale n which is smaller than ADS scale, that means then you've put in explicitly a factor of n into the metric, and you shouldn't think of solutions or metrics which have factors of n explicitly, because n controls quantum fluctuations. So if you put n explicitly into a classical solution, that becomes a bad classical solution. That's not a good coherent state. When we talk about coherent states, we never talk about coherent states which have explicit factors of h bar in them, right? Because coherent states, we don't try and localize points in phase space to within an accuracy of h bar.
But you can only have a big system.
No, you cannot, because then they stop being coherent states. Coherent states have the property that they're almost orthogonal. You don't talk about coherent states that are within h bar of each other. So you never put in h bar explicitly into a classical solution.
Okay, so what I don't understand, I have a geometry. The geometry is due to some operator at orbital point.
Yes.
How can in principle
I don't know what it means for the geometry. Geometry is dual to some state at the I don't know. Yes. So in that there's a state and you change the model I continuously and you come to this. Okay, fine. Yes.
So the question is, how can I ascertain that you have quantum fluctuations? At this point, I only have.
I cannot ascertain.
In the two-chart system, it's clear there's a quantization.
I can't.
In the three-chart system, it's just
I can't ascertain.
I don't have any calculation.
Yes, that's correct. I don't have any calculation, but I can only do the calculation once you give me the quantization. But I'm making the following rule of thumb statement, which is that in general it's a bad idea to put in factors of h bar or put in factors of n explicitly into the metric. If you do that, your metric becomes unstable to quantum fluctuations. Then you expect, if you have features in the metric that depend explicitly on n, then
the only ingredient is a long throat.
Okay, so maybe we can. Sorry.
I just had
let me just conclude and then yes. Sorry, go. Yes.
Coming back to my question
Yes.
about the observables.
Yes.
So the statement about no explicit factors of n.
Yes.
You also not wanted. So you've argued before that you can actually use bulk observables.
Yes.
But you case,
Yes.
you don't want the geodesic length to scale with n because the same comments about no explicit factors of n would appear.
I don't want I don't want geodesic length to scale with n. I don't know geodesic length.
You pick some very special observables.
I'm picking the observable which is the metric at the bottom of the throat. You see, the only question I'm asking is.
That's not a very natural CFT observable.
It's not a natural CFT. It's a yes, but it's a natural bulk observable. You see, the question I want to ask is: are these long throat solutions? Are they reliable? Are they reliable indicators of what happens to an observer when he goes in?
The question is, can you trust that sort of observable when you make the geodesic length?
What do you mean trust that sort of an observable? It is an observable in the theory, and the question I'm asking is that solution a robust solution against?
You've constructed in the bulk theory, and you're telling us that you cannot trust the bulk theory when there are features in the geometry or whatever that scale with n, right?
So I'm saying that and so indeed, so there's another solution which doesn't have this problem, which is just the conventional black hole solution, and I claim you should trust that solution rather than looking at these solutions which are unreliable because they have explicit factors of n in them. I claim that if you want to look at what happens in the interior of the black hole, you should look at this. Okay, let me just conclude and then we can continue this discussion. I don't have a calculation here because I don't have a quantization. If you give me a quantization, I can try and compute quantum fluctuations. This is the statement that, the statement I was making was that if you have these long throats are amenable to fluctuations. They can very easily get destabilized. I mean, that's the statement. If you try and make the throat very long. I think that statement is intuitively true, but I can't make it more precise till you give me a
But that's
quantization.
again maybe throwing elephants on atomic force microscopes.
And the question is, what happens to an observer when the observer dives into the black hole? That's the question I'm really interested in asking.
Then it shows everything, of course, but that's not what.
So what is the relevance of the fact? Well, okay, let me just say something about the large momentum thing, and we can come back.
And even the black hole by itself actually changes. When you have an observer throwing in the black hole, the extremal black hole, even the extremal black hole itself actually.
Yes, it's true. The extremal black hole itself might get destabilized, and maybe some singularity will form. It's true. That's just because the inner horizon comes and hits.
Yeah,
That's true. So it's true that the extremal black hole itself might get. Okay. Let me just say one more thing about this thing, and we can come back to this. Okay. So here's the large gamma calculation. So most of you have probably forgotten, but at some point I said that the Weitman function has to satisfy a bound. It has to fall off at least as fast as e to the minus beta gamma by 2. In these fuzzball solutions, you can calculate what the fall off is, and the fall off is too fast. Okay. In fact, the fall off is too fast again by this factor of kappa that we were discussing. Okay, so at least for these solutions which have JR not 0, this fall off is too fast compared to the black hole. Okay. So you can take the black hole which has JR not equal to 0, you can compare what the fall off is there, you can compare the fall off is for the fuzzball, and the fuzzball fall off is too fast. So the fuzzball is not saturating the boundaries of the black hole.
So again, what's the black hole?
This is the difference. The difference between the fuzzball exponent and the black hole exponent is this.
Yeah, but that's 1 over n suppressed. Right?
It's 1 over k. This n is small n. It's not 1 over capital.
K is, yeah, but k is 1 over 5.
Now let's take JR to be large. So now since you wanted to look at,
those are again, they're not even.
but you can't have it both ways. You can't say that the JR solutions. You see, so you said now let's look at it. You're right. If you look at these solutions, I don't want to go back to the discussion of taking solutions which have k being very large. So let's look at the reliable solutions which we all agree, which are solutions which have some fixed value of JR. For fixed values of JR, okay, so for those for a given non-zero value of JR, do you agree that the microstates you have found are not typical?
When there's no ADS to throat, of course they're not typical. Also
Okay. Okay. So
I don't know what the problem is there. We've been saying that in all the papers. Since we give the exact CFT state, you know exactly what the Strominger-Vafa states are.
It's not clear what the exact CFT state is something I think that computing 1-point functions, yes, but computing 1-point functions is not enough to fix the CFT state. It gives you a guess about what the CFT state is, but computing 1-point functions and matching that with the orbifold point and saying that's the exact CFT state, that's something I'm skeptical about.
Have a throat and the black hole has a throat. The state is typical.
Okay.
The state has J right is equal to like
okay, so it's okay.
Black hole has J right is equal to 0, of course.
Okay, so it's true if you take k to be.
Black holes don't have any J right. So
yes, it's.
If you want to compare in the same regime,
okay,
the
so
black hole has J right is equal to 0 compared to the fuzzballs which have J right is equal to 1 or something.
You can go to that regime where k is large and then this gap becomes small, and then we'll go back to the discussion of whether these solutions are reliable or not.
That's a discussion again. That's
Fine. Okay, yes, but so anyway, this is the difference.
Compare apples and apples, meaning like black holes with J is equal to 0 or like maybe 1.
Well,
fuzzballs with J is equal to 0.
Okay,
so you are comparing apples and oranges. Fuzzballs with J equals to n.
With black hole with JR, I'm computing also black hole with the same value of JR. I'm not comparing this with black hole.
The same value of JR. The black hole doesn't exist. There's no supersymmetric black hole.
There is a black hole with that value of JR, which is the Sweaty-Larsen black hole. It's fine, but there's not nowhere which I didn't rely on supersymmetry. There is some black hole with that value of JR, which is a Sweaty. Okay, so supersymmetric, but there's a black hole.
Sure, but why? Then I don't have the same energy. I mean, the fuzzball is here, the black hole is here. So if you are to say that the fuzzball doesn't move for a black hole, you have to set up the rules of the game. What's the energy?
Okay.
What's the temperature? What GR?
Sorry,
what are the
can I understand what is the
We
significance
don't
of the
have-
solutions?
then we discuss.
What is the
Here we are
significance?
comparing
What is the
fuzzballs, here we are
significance of the
comparing
parameter
fuzzballs.
A in your? Okay,
Sorry?
can I understand what is the significance of the parameter A in the solutions that you?
So I have a GR.
Yes, and what is the
more-
significance of that GR?
The more the black hole, so for example, if you look at the mass gap, which is again my friend, the mass gap when you have the solution which has GR is equal to 1/2, the mass gap is exactly 1
So,
over
but
n1 and
what is
5.
the relevance of? Why do you even introduce the parameter A? Why don't you just set A equal to 1 over n1 and 5 from the start?
No, because I have a much bigger family of solutions.
But what does that family? Does that family of solutions have anything to do with the family of solutions with A not equal to 1 over n1
Yes.
and 5 have anything to do with black holes or not?
They are also states of the black hole, sure. And
But
that's
they are
the
states of the
same
they are
They are states of the
Sorry, we
CFT.
can stay away from J rights being of order h bar by making A macroscopic, but I think I can make the right-hand side of your expression still go to 0 with that constraint.
by taking n small n very large.
Yes.
Yes, you could take small n very large, and this would go to 0.
No, it's not small and very large. You know, it's actually.
You could take small and very large.
Here
Well,
is
also
G right.
kappa you can make large.
Kappa is B by E. So kappa
No, but
well.
kappa is J right. Again,
Kappa
kappa is J right. So
that's
again,
right.
if it's,
So-
sorry,
so- so
one
let's-
over J right.
let's
So
compare-
If 1 over J right is so if J right is macroscopic, then there's no black hole in that J right. The black hole doesn't exist. And then we're comparing apples and oranges.
J right was A.
No. J right is A over B. So it's actually.
Okay.
You know, in his language it's kappa.
Okay, J right is just A, right? It's is it A? It's
It's an
n into B.
it's
Yes,
one
fine.
over B.
Okay, good.
Yeah, so I
Fine.
can fix that, right, and then I can take n to be big.
No,
So-
but you don't have to take that to be big. The moment you choose J right to be the black hole J right. So there's no black hole which has J right is equal to n. The black hole doesn't exist.
Which
The
has
only
J right
black-
is equal to?
to n and 1 and 5 or any number which is over the 1. The only black hole which exists on the planet is the one which has J right is equal to 0, and maybe quantum effect you can say maybe 1/2. And that black holes don't have J right. Black hole solutions, supersymmetric black holes have J right is equal to 0. The BMPV black hole has J1 equal to J2.
Good,
In
good,
4
good.
dimensions, J right is equal to 0. If you want to look at microstates for that black hole, you can say maybe I have some quantum effects and some 0 modes and so on and so forth. Maybe it's not 0, maybe it's, Ashok has been writing papers over the past 10 years saying that. So one of the big objections to that our solution was that we have a J right. So when you have a huge J right, there's no black hole which exists.
That's
So
because
when
it
A or
violates is bound. That's because you want L0 being JR squared by n,
Well,
right?
you have a supersymmetric solution. There's
Sorry,
no
but-
supersymmetric black hole with J right is equal to 0. If you break supersymmetry, then you have a black hole which is which has a much bigger energy, and you're comparing it with a fuzzball which has 0 energy. But then again you have apples and oranges.
Sorry, just one second. Let me just try and understand. So there's a bound which is
BMPV.
very good. But let me just understand. So you need to satisfy this bound.
That's the entropy bound.
That's
No,
there's some bound
no,
that's
no.
just
The
coming.
supersymmetric black hole has 0 J right.
Okay, good. But let me just understand. What is once again? I just want to understand what is the significance of the solutions that you find in your paper which have non-zero J right?
So the CFT on the other hand doesn't
Yes.
have 0 J right.
Okay.
So in the CFT you can build states like black rings, for example,
Yeah, very good.
solutions, black Saturns, and so on and so forth.
Okay,
which don't
good.
have a 0 J right.
Okay, good.
And
You
those
can
states also
compare.
have a lot of
You can
entropy.
compare in the CFT, just in the CFT, just by doing a computation in the CFT. You can ask, does the CFT saturate this large gamma bound at thermal temperature? This doesn't have to be a black hole calculation. This is a bound from the CFT, and the
But
fuzzballs do not saturate it bound. This is a calculation. So this is a calculation you can do just from the CFT. You can ask in the CFT.
But then you're
In the CFT, are you saturating this large gamma bound? And it's a fact that black holes saturate the large gamma bound, but you can simply ask in the CFT. Well, so in the CFT on the plane, for example, you can in the CFT on the plane you can just compute this 2-point function just by using modular invariance at thermal. So you can compute the for the CFT. This is the CFT on a torus, but the CFT on a plane you can just compute the 2-point function using modular invariance, and you can check that this is indeed the fall off of the 2-point function. Okay, and the fuzzballs are not saturating that fall off; they are above that
But
fall
they're
off.
not the right fuzzballs. Again, they are fuzzballs which correspond to black holes. So again,
So-
the CFT they are different. They are different. So okay, where do you look
Okay.
at the CFT? The orbifold point or somewhere else?
This is this calculation actually doesn't change because the calculation that just relies on the 2-point function of the primary operator computed and then using modular invariance to fix it. So this calculation actually is the same. This calculation of 2-point function of CFT operators in a plane doesn't matter. It's protected, and it saturates it saturates this bound at all points in the modular space. It's a 2-point it's a thermal 2-point function. So it's a thermal 2-point function you can compute using modular invariant. Why?
I mean, again, can we stick to zero temperature?
It's a thermal.
J right is equal to 0
But
plus or minus
sorry,
1.
thermal 2-point function is because you have beta r. You have one temperature. So there's a left and a right sector. You set one temperature to infinity, one temperature 0. The other temperature can be kept finite. This is a calculation you can do. At least in the plane, you can do this calculation.
But in the CFT, again, I don't know why you have to compare a fuzzball, which is basic, which has J right
With some CFT state, you should compare it with the CFT calculation. You're claiming it's a CFT.
J right is equal to 100, sure.
Yes,
Which is
but
not the black hole.
yes, but the CFT state at for those values of charges satisfies a certain bound for the fall off of the 2-point function, which the fuzzball doesn't satisfy. Which says that the fuzz.
CFT state with J right. Where's the J right in the CFT?
What do you mean? Where's the J right in the CFT?
So there's a CFT calculation. The
yes.
one calculation I see is the one for the black hole, the one with gamma.
Actually, good, very good. The CFT very good.
So there's no CFT calculation.
No.
The
CFT.
People can do it. There's a calculation which could be done.
Let me just actually let me just say one more thing. So indeed, well, you're right. So you could do a CFT calculation. The CFT calculation just depends on beta L and beta R. It just depends on these two temperatures. It in fact doesn't care about JL. You're right. It JR. It just cares about beta L and beta R. You can do that CFT calculation. That CFT calculation has a certain bound which the fuzzballs are not saturating. So which says that the fuzzball states are atypical states. They.
No, but again, you have to either compare to the black hole. So
No. Why? Let's compare to the CFT. Let's compare to the CFT where you can compute on the plane. Now you might say that on the torus things are different. Maybe that might be an objection you might want to raise. But for large gamma, you probably don't care about whether you're on the torus or on the plane. Let's just do a CFT calculation. You find there's a bound. The CFT
is macroscopic.
It doesn't matter.
No, it does, because my strings, for example, they cannot have momentum anymore on them. So again, if you think about the D15 CFT,
this is actually this kind of calculation. This is this kind of calculation is just fixed by modular invariance. Thermal 2-point functions in the CFT are just fixed. And they just fixed. They just fixed. Thermal 2-point functions of primary operators are just fixed. They don't care about all of this. And there's a property about these thermal 2-point functions that these fuzzball states are not fixed. There's some bound in some limit. They don't care about J right. I don't know why.
There's a black hole calculation.
Yeah. Okay. Maybe you can just compute. Okay. Okay. Let me just. So anyway, this is the answer. We can go on. Let me just say we can verify this answer numerically. So there's some numerical calculation. There's WKB answer. These things match well. So this was the conclusion. At least if you take kappa to be order 1, which is what we are discussing, these Weitman functions fall off too fast. They fall off too fast when you compare, with some. If you compare with black holes at the same beta L and beta R, but you can, as I said, also do some CFT calculation, and that means that these fuzzballs are microstates. They violate eigenstate thermalization. At least they don't behave like the thermal state. Now I said at the beginning of this talk, I don't want to assume eigenstate thermalization. So, and remember this bound I proved was a bound between theories. It was a bound that holds in any relativistic theory. I'll just be done in 2 minutes. And so, this is not by itself a contradiction if you don't assume eigenstate thermalization. But let me say that we already have a strange conclusion, because it says if these fuzzballs are microstates, there must be some other geometries that that have the same charges that oversaturate this large gamma bound, so that when you average to get the thermal ensemble, you get the right average, but I don't know of any geometry that oversaturates this large gamma bound. So if these fuzzballs are microstates.
The more simple solution, those guys again are just very atypical. They have a large A, right?
Yeah. So they're very atypical. But are they very atypical also in the CFT? They're very atypical in the CFT also.
Yeah, because J right, the CFT is not atypical J right.
No. The CFT has states with J right. Has many states with J right. Are these? It doesn't matter. But you can focus on the subset of the CFT, subspace of the CFT that has that value of J right.
Yeah,
now, are these?
No,
of course you can compute the Weitman function. As I said, the Weitman function is fixed by modular invariance. You don't care about this, right? You see the Weitman function is very simple to compute. You have two primary operators. You compute it on the cylinder, and then you use modular invariance to say, that's the computation on when you have some temperature. So that Weitman function you can compute directly.
But how much entropy? So clearly, if I look at states which have J right is equal to 100,
yes,
then I can get some entropy out of them. Using black rings, I have other ways to get entropy out of them, which don't involve these particular microstates.
Okay.
Now, do you claim that for those black rings, for example, if I compute the Weitman function, I get a very different result? Because again, this expectation that you have this operator and you have this thing near.
For these black rings that I would in fact I would suspect you would get a result that would probably saturate this bound, but I haven't done this calculation. Maybe. in the CFT you do have a result that saturates the bound. So there should be some, there should be some
but I think this just agrees that J-right microstates are not the ones with the black hole. I mean,
the J-right microstates are not typical ones in the CFT. They are some atypical set of states. It's not a question of black hole. They're just not typical states in the CFT. They're violating eigenstate thermalization. These states, and I suspect actually the states which have large kappa are not reliable for other reasons.
But that's okay.
But I suspect that the states which have kappa equal to order 1 are just atypical. They're violating eigenstate thermalization. Okay, but they violate. They're atypical in the CFT. Okay, so sorry. Let me just conclude. Okay, so this is the discussion we're having. I suspect we don't agree yet, but I claim that fuzzballs that vary at order 1 distance from the black hole. Fuzzballs which vary, which are these solutions which have A, and this is true for non-extremal fuzzballs. As if you try to find fuzzballs corresponding to that, they cannot represent black hole microstates. The basic intuition that I tried to argue in the last part of the talk was that you can detect this difference by looking at simple 2-point functions. So at the moment you have fuzzballs that vary at order 1, you can detect this difference by looking at 2-point functions, and these 2-point functions then fail to satisfy eigenstate thermalization, and they fail to satisfy the bounds that you expect that black holes satisfy, and so they cannot represent black hole microstates. And therefore, if fuzzballs have to represent even a basis of black hole microstates, they must vary only Planck length outside the horizon. We discussed this a lot at the beginning. Maybe there might be some other length scale which appears, which you have to tell me. But in such geometries, and we've again had a lot of discussion about this, I claim if you try and make these throats very long, or if you try and make some fuzzballs that cap off that have Planckian structures, then I claim that that mixes up classical and quantum. The moment you try and write down metrics which have Planckian structures, I think that makes quantum fluctuations large. It makes these solutions unreliable. At least in one case where you look to these two-charge solutions, you could see if you try to write down metrics which had Planckian structures, the metrics became unreliable. Okay. Now maybe in that setup there's some other frame you can go to, but in the setup where you have a classical horizon, that solution doesn't have this problem of having large quantum fluctuations. Okay, but of course I should say that all these problems arise only if you insist on fuzzballs as representing typical black hole microstates. Okay, if you think of fuzzballs as stars in string theory, as some set of interesting states which have the same charges, then they're an interesting class of solutions. I think there's a lot which is interesting and clever about fuzzballs, but I think that you shouldn't think of fuzzballs as typical black hole microstates. Okay, so I think I'll stop here. I think we had a lot of discussion. And yeah. Okay,
Okay, so any
Sure, thank you for sitting through the talk.
Okay.
Thanks, Anil. Thanks, okay. You have a question? Yes.
Suvrat, you can speak now.
Are we still recording?
Do you actually have a question or
I can ask.
Sure, you can ask, yes.
Later, but okay.
Go ahead.
But I just saw, other than trying to construct the solution,
Yes.
usually every fuzzball talk has this motivation that you should not look at this just black hole geometry because
Yes.
of this small correction theorem.
Uh-huh.
So, do you have something to say?
Yeah, the small correction theorem is wrong. It's wrong because it assumes exact locality. The small correction theorem, which is the theorem that Mathur came up with, assumes that you have strong subadditivity. So let me just remind those of you who don't know this theorem. You take a black hole, you take some region inside the black hole which is C, you take some region outside the black hole which is A, you take some region which is far away. You look at an old black hole. If you have an old black hole, you can look at the entanglement entropy for A. It's supposed to follow this page curve. It goes up and goes down. Okay. The fact that this time is called the page time. The fact that the entropy is going down at late times says that A is entangled with B. Okay. The fact that the horizon is smooth says B is entangled with C, and the fact that A is entangled with B and B is entangled with C violates the strong subadditivity of entropy, which is the statement that SAB plus SBC has to be greater than equal to SA plus SC. Okay, if A is entangled with B, then SAB is smaller than SA. That's what's happening here. Okay, and if B is entangled with C, then SBC is close to 0, and that's violating this strong subadditivity. But the strong subadditivity of entropy assumes that the Hilbert space factorizes between A and B and C. Okay. In particular, and this is something you can see very explicitly in empty ADS. if the Hilbert space in C, if the degrees of freedom inside the horizon, by the way, this is the horizon. Okay, this is the horizon. If the degrees of freedom inside the horizon are constructed as scrambled versions of the degrees of freedom of A, if they don't commute with degrees of freedom on A, then this inequality just doesn't hold. Now, the fact that there's this version of black hole complementarity, the degrees of freedom here can be written as complicated scrambled versions of degrees of freedom of A. This is not some abstract statement. In empty ADS, you can make this totally precise. If in empty ADS, you could set up the same paradox in empty ADS. Let's just do empty ADS. Okay? And let's look at a time band of some length t. This is a paper we wrote with Kyriakos Papadimos a couple of years ago. And let's take this t to be smaller than the light crossing time. Okay? If you think of an observer on the CFT who limits himself to this time t, then this observer in the CFT can actually see only a limited region in the bulk. Okay? That's because the light cone only extends to a limited region in the bulk. So it looks like a horizon has emerged in the bulk. Now that's because by force you extended the CFT observer to see only a limited amount. But in fact, if you can show explicitly, if the CFT observer uses arbitrarily complicated operators in this time band, then this observer can also construct operators here. So in fact, operators here can be written as scrambled versions of operators here. But these operators are very complicated versions of operators here. Okay. So in fact, it's explicitly true. You can show that the Hilbert space of degrees of freedom here does not commute with the Hilbert space of degrees of freedom here. In this toy example, you can just see this. In fact, in this construction that we had of the interior, it's also true that Hilbert space of C is not independent of A, and then this just doesn't hold. Okay, so the small connection theorem is based on this, and it assumes that quantum gravity is exactly local, which is just not. You can see in ADS CFT it's just not. So I don't think you need fuzzballs to solve the information paradox.
Still, yeah, so maybe you don't need, but you can still imagine a version. I mean, if these fuzzballs are sort of very stringy or very, not classical, then it could be that they led to an effective theory where there is some variation of localities.
But can I say that the small correction theorem was invented because I think Samir's perspective, I may be wrong, but I think the perspective was that the solutions, the classical solutions, are not powerful enough to tell you what happens to the generic microstate. And he wanted an argument to argue that the generic microstate does not have an interior, that the generic microstate doesn't have a horizon. That was the reason for inventing these. So I think this is not a valid argument because of this fact that the Hilbert space doesn't factorize and the small correction theorem assumes locality. So I think the argument that fuzzballs are required for resolving the information paradox is not true. In fact, there are many. Yeah.
But you can say string theory will give an answer at some point if you have a super.
I think. But there are these calculations of one way of phrasing the information paradox, for example, is to look at the long time decay of the 2-point function. The fact that the decay has to get capped off at e to the minus s by 2. So you can do some calculation, as many people have done. Kaplan and Fitzpatrick and many others have done, which is just a calculation you can do, and it says that basically effective field theory doesn't break down at any point. It's just that effective field theory is not good for computing these exponentially small corrections. So to have you can resolve the information paradox with exponentially small corrections, and for that you don't need effective field theory to break down at order 1 scale at the horizon. If the fuzzballs is made up of, if the fuzzball represents typical states, you have a problem because it suggests that effective field theory is breaking down at order 1.
So what correction to Hawking's calculation do you need in order to
the correction
make it correct?
The corrections you need are exponentially small corrections in the density. It's the fact that so if you take the density matrix that you get from Hawking's calculation, which is a thermal density matrix, and you add exponentially small corrections to all of its terms, which you cannot compute reliably in effective field theory, you could turn that density matrix into a pure density matrix. It's a version of the theorem I was describing earlier, that pure density matrices, pure states and mixed states look exponentially close to each other if you probe them with simple observables. So effective field theory is good for computing low point correlation functions of light operators, which Hawking did, and he got the right answer, which is that they behave thermally. But that's very different from saying that the full state is thermal. The full state is still pure. So I think this question of what is the correction you need, the correction you need is something that is not captured by effective field theory. It's an exponentially small correction, which you may be able to compute maybe in ADS CFT in some setup. But
in principle, you would also.
So does that answer the question, or yeah?
Sorry. how do you compute this exponentially small correction in string theory in the bulk?
In the bulk?
Yeah,
I don't know how to
abstract,
compute.
I mean, just in principle, just-
I don't know.
I was trying to understand whether there is a
I
contradiction.
I don't know. I don't know how you compute them in the bulk. There were these proposals earlier by Maldacena that there's some other saddle point, but I think those are not the right way to compute them. But I don't know how to accurately compute the exponential. I think we need to understand bulk string theory much better to be able to compute these exponentially small corrections. But I don't know how to compute them.
Do you actually mean string theory or you mean quantum gravity?
Well, it's just string theory, quantum gravity. I mean, and isn't that string theory or?
No, because I thought, I mean, you're
Yeah. I don't mean classical string theory. I don't mean classical string theory. You need you need to understand the full string theory in the bulk in some way to compute these corrections. I don't know how to do that. But I think you don't need order 1 corrections to Hawking radiation or to effective field theory to fix this. You need exponentially small corrections, which we have to find some way to calculate. In the boundary theory, you can compute them, right?
Any other questions?
Okay.
We can't extend for a fourth hour.
Well, we're slightly less than 3 hours, so if you go on for another 5 minutes.
No.
Okay.
Okay.
Well, let's thank Suvrat again.
Thank you.